to all of you. So it's a pleasure to welcome, I think there will be many more people who are going to join in. So it's a pleasure to welcome all of you for this third edition of the Reinforcement Learning Workshop being organized by the Department of Computer Science and Automation at IISc. And it's over the next, this started yesterday with the tutorial session by Professor Guhan Thope, and then over the next 2.5 days starting today, we'll have talks by very eminent speakers on the kind of work they have been doing and so on. So it's going to be extremely informative, and probably you will be able to gain a lot as students, even as faculty and so on. So to inaugurate the workshop and speak a little bit about the Department of Computer Science and Automation, we have the good fortune of having Professor Vinod Ganpati, the department chair, with us. So may I request Professor Vinod?
Thank you, Professor Shalabh. Good morning and welcome to all. It's a pleasure to have you all here. And on behalf of the department, the first thing I should do is to thank our sponsors. So this workshop is presently in its third edition. We have had the opportunity to invite several of you, several students, and several eminent speakers. So all this is, of course, made possible by Walmart, who has provided a very generous multi-year grant to the department that funds a variety of research projects. It's called the Walmart Center for Technological Excellence in Algorithms and Learning, and it was inaugurated in April 2024 formally. Extremely useful when industry brings such generosity to academia. So it's elevated our research capabilities in foundational research with translation impact. In fact, it's funding 8 of our faculty members and several postdocs, several students. They can travel, they can organize workshops like this. So many thanks to Walmart for this. Many activities that have been going on. This workshop, of course, but there are Walmart PhD fellowships, postdocs. I'll tell you a little bit about our pre-doc program, which students are welcome to apply to. And we have been having several algorithms and geometric algorithms, graph theory workshops, especially in the winters, and we also have outreach events in the summers usually. So with that, let me tell you a little bit about our department also. As the host department of this event, I was hoping that I can familiarize you with some of our history as well as our current work. So the department started in 1969, so we are 57 years old this year, and we are proud that the department is doing well after despite its age, or thanks to its age. We are the top ranked computer science department now in India based on this website csrankings.org, which measures output in flagship conferences, and we are the only CS department ranked in the top 100. This is as of 2024. And of course, there's a global presence of our department's faculty and students in all of the flagship fora, conferences, journals, and so on. And our graduates are also highly sought after nationally and internationally. As a department, we focus on 3 broad areas of work, AI/ML, of course, computer systems, and theory. And this slide here just shows you a sampling of various research projects that are going on in the department. This is by no means a comprehensive overview, just a sampler. Several of my colleagues also work on interdisciplinary areas that sort of cut across these streams. We are 25 faculty members, with one coming in next year as well. And what you see on the slide are basically the places all over the world where our faculty have undergone their training, and really distinguished group of colleagues I'm fortunate to work with. Of course, we couldn't be prouder of our students. Just a small sampler of some of our recent PhD graduates who have all gone on to do very well, gone on to pursue successful research careers of their own. As you can see here, some of our former students have also gone on to win be runners-up in the ACM India Doctoral Dissertation Award competition. Back to my colleagues. We have several award winners among our colleagues. So just three examples from the ACM India Early Career Award Series that was instituted in 2020. Last year, my colleague Arka Prava Basu won it. The year before that, Siddharth Burman. In 2020, my colleague Uday got the honorable mention. And just to continue along the same lines, this year we were fortunate that our colleague Arka Prava Basu was recognized with the Rashtriya Vigyan Yuva Puraskar, previously called the Shanti Swarup Bhatnagar Award. And of course, Professor Shalabh Bhatnagar here was elevated to the rank of IEEE Fellow last year. I think last year it happened just in time for the workshop. So congrats to all of my colleagues for this. Finally, some opportunities for those of you that are students in the audience. So the CSA department, of course, has its PhD, MTech programs and so on, which you should definitely apply to. But for those of you that are finishing your undergraduate degrees or finishing your master's degrees, and you may have thoughts about pursuing a career in research but are not really sure, we have a program called Sparks. It's called Scholars Pursuing Advanced Research in Computer Science. The basic idea is that you come and spend a year or so with a faculty member, and the faculty member pays you through grants, for example, like this Walmart grant, and you can see if research is a cup of tea, right? And you can try it out, work with a faculty member for a year, maybe get a publication or two, and then decide what to do further with your future. And so this is a program that our department has been, we have been recruiting, we have been soliciting applications for the Sparks program over the last couple of years. The call for Sparks goes out twice a year. So please keep an eye out on our department webpage for the Sparks call. And if you're interested, please, I encourage you to apply. So with that, let me conclude. Organizing a workshop like this, of course, a very vibrant experience for those that attend, but it's also a lot of work on the part of the participants, on the part of the organizers. So many thanks to Professor Guhan and Professor Shalabh, and of course our staff, Kushal, Akshay and Sanjay, who are helping organize this and taking care of all of the logistics. So with that, let me welcome you all once again, and I hope you have a very nice 2.5 days.
So on behalf of this workshop, I have great pleasure in giving this presentation. Yeah, hello, Furong, are you here? I can see muted. Professor Furong?
Yeah, yeah.
Yeah, so good morning, everyone. So it's a pleasure to have Professor Vivek Borkar as our, he's our inaugural speaker today because the inaugural speaker didn't show up. So Professor Borkar is a very well-known name, not just in India but everywhere. So I mean, to formally introduce him, he did his BTech, MS and PhD from IIT Bombay, Case Western University and University of California, Berkeley. That was in 76, 77 and in 1980. And then he has held positions in TIFR Center for Applicable Mathematics, IISc Bangalore, TIFR Mumbai, and then TIFR IIT Bombay. He currently is the National Science Chair at IIT Bombay, and he has written several books. We follow many of his books as well, particularly the one in stochastic approximation is really something that extremely noteworthy. So with those few words, may I invite Professor Vivek Borkar. His talk is going to be on nothing comes from nothing.
So thanks for the invitation. And I have to explain the title, I guess. So it's actually from some verse by this character called Richard Rogers. Is part of the Rogers and Hammerstein team who used to write Broadway musicals. And I have changed the last two lines of this. And the point I want to make is that this is the translation into ML lingo. So there are many interesting things one observes, and they're sort of written off as quaint phenomena or something bizarre happening. But one can actually dig into it and give some mathematical justification of it. So that's my plan. So there's a whole laundry list of several topics I'm going to. They vary both in sort of level of math needed and the nature of the problem. That's why I picked the bizarre title, so that I couldn't think of anything common for all of them. And one warning is that there are stylized models. I mean, when you try to explain something mathematically, generally it's kind of idealized. Otherwise, you can't really go far. Yeah, so first is this collection of things which, I mean, clocking, temporal double descent, and catapults. So let me maybe just show the figures which are drawn by a kind student for me. So this is what's called the double descent, which actually usually the x-axis is not, the classical double descent, it's the number of features, not number of iterations. But there's a sort of a cousin of the original double descent called temporal double descent. There's some work in that as well, where as time goes on, you see this, the error drops, increases, drops again. The second one is grokking. So the red is actually a training error, and as the test error, it decreases, goes flat, flat, or I mean, it doesn't decrease basically. It can even increase a bit and so on, but it's more or less flat and then decreases again. And this is something where this happens multiple times. That's called catapults. So roughly this kind of phenomena, why this happens. And it's a stylized model which uses something which used to be a folklore, and it's not a folklore anymore. That's a little known fact. That if you take a function of a large number of variables with bound on its Lipschitz constant, or maybe modulus of continuity, that actually non-trivial constraint, and therefore what it forces the function to depend mostly on a subset of the variables. And just to get intuition, if it's Lipschitz, it's almost everywhere differentiable. So Lipschitz constant will be basically the essential supremum of the gradient. And if it's bounded, then not all of its components can be very large. This is not a proof, but just to motivate. Theorem is it's kind of it's proper theorem in this paper of Tim Austin, which I'm not going to state because I'm using this just to justify the model. I won't be using this theorem. So stylized model is basically, I am assuming that the variable split into two parts. So it's x comma y. So it's a d-dimensional variable, which is some first, I forget what some first r components I call as x and the rest as y. And the function is this from f of x comma epsilon y. So this means that it depends largely on x and less so on y. Then if I write SGD, this epsilon pops up for free. Pops out in the second iteration. I don't see the, here, okay. so it becomes a two-time scale stochastic approximation on its own. I mean, I am not designing I am just using naive vanilla stochastic gradient. I am not making it two-time scale. It happens because the two variables have different sort of scales of dependence. So I stick to the simpler case where everything converges when you want it to. Just for simplicity, one can do more general things with a lot more complicated notation and so on. So the idea is that because epsilon is much smaller, xn updates move faster than yn. So you can analyze them by treating yn as practically a constant. And suppose I treat yn as a constant, assume that xn converges nicely to some lambda of y, which is Lipschitz. That, and I won't get into the assumptions and so on. But suppose it converges to lambda y. What it means is that xn minus lambda yn approximately converges to 0. I keep saying approximately because these results are almost sure for decreasing step size. I'm using constant step size as is the standard thing in ML. So for ML, everything, all the convergence claims I make are approximate. What it means, it will concentrate around that point. So here, last statement says it will concentrate near 0. So this is basically the fast descent. I'm treating yn as slow, xn decreases fast. And that means eventually xn is kind of close to lambda yn. So grad x of fxn yn is approximately 0 because fixing yn xn is more or less tracking the corresponding minimum. And therefore lambda y of f of xn comma yn is approximately lambda y, sorry, not lambda, sorry, lambda. Grad y of fxn comma yn is approximately grad y of f lambda yn comma yn because xn is approximately lambda yn. So if I plug in the the grad y, the right hand side in place of the left hand side in the equation, I have a self-contained iteration for y. So this left minus right will be another small negligible error which I club with other errors. So I can analyze y. It will just self standalone iteration for yn plus some negligible stuff. It will converge to the minimum of f lambda dot comma dot. And this is the slow descent. This is a standard two-time scale stochastic approximation. Now the claim on and this is I'm just going to say in words, there will be some middle region where these two terms are comparable. That's because if see when because the faster time scale is minimizing over x, the grad x fxn yn will is much smaller than grad y fxn yn. So if that difference of scales is enough, so if it's grad x is epsilon times grad y, then they become comparable. Okay. So that's where you see all these funny things happening. That's the claim. Okay. So I'm not see. There's also a different issue. Sometimes you want it to go all the way. Sometimes you don't want. There are some. So for example, there are situations where the second descent means you are actually modeling the noise as well. You don't want that, and there are people who propose stopping criteria, early stopping, and so on. So I don't want to get into that. So if you don't dig into the details, this is what you expect just because of the scale separation. So that's the first thing. And second is something called collapse in generative model, and this is assume some abstract space S, which is basically given a footnote, complete. It's a separable space with complete metric which is compatible with it, with its topology. This is not for not for fun, but one needs that level of generality. So it's called a Polish space. Didn't say so because a lot of that was done in Poland long back. And the reason it's useful is that most of the classical probability theory, the theory of probability measures, which you can do on RD, a lot of it goes over to Polish spaces. And it includes, of course, Banach spaces, Hilbert spaces, so you don't have to think again. That's one advantage. And the even more bigger advantage right here is that space of probability measures on a Polish space is a Polish space. So whatever I say as though it's a RD, I will talk about a PS valued Markov chain, and it's legitimate because it's Polish. Okay, so the generative model, of course, the other reason is that generative models, you are working with space of continuous functions on 0t with max norm. That is a Banach space. That's not a finite division space either. So but it is a Polish space. Yeah, yeah. So I'll come to that on the next page here. This is the general sort of generative model. You basically use your current collection of samples to generate the next sample. So you can suppose at time n you have this xn sub I models where capital N is very xn sub I samples where I goes from 1 to n, where n is quite large. You use that, you fit some distribution on that and generate new samples according to this distribution, and then fit another distribution under that. The classical version I mentioned on the next slide is just that you take the empirical distribution. That's the simplest, and the analysis is also almost trivial for that. But I have also seen, for example, Andrew Thangaraz uses some parameterized fit and so on. So he just modulates the test Gaussians and modulates the, I think either mean or variance or one of them. I don't remember now. So this is the classical thing. You take empirical distribution at time n, generate new samples using that as the distribution, and take empirical distribution of a new samples, call that mu n plus 1. Then what you get is just by construction, that first equation is true. Now, if that's true for A, it's a kind of standard approximation argument tells you that it's also true for functions. So from this first equation, first display, I can go to the second display, it's a classical major theoretic argument. So integral f d mu n plus 1 conditioned on everything up to n is integral f d mu n. And that means that it's what's called a martingale. And then because it's bounded for free, f is bounded. So, huh? Oh, sorry, that's a mistake. There may be typos here and there. Yeah. Should be f. Yeah, so it's a bounded martingale, so it will converge with probability 1. And this last statement you have to take with a pinch of salt. So if it converges with probability 1 for all bounded continuous f, then the last statement is true from definition with the kind of topology one puts on PS. Now there's a catch, so slightly technical stuff for those who want it. So it's enough to consider not all f, but f belongs to a certain chosen countable class, f sub I. It's called convergence determining class, so that if you test it for those FIs, that's enough. And the advantage is that because it's countable, you can pick a common zero probability set, because countable unions of zero probability sets have zero probability. And outside of that, it will be true for all FI. That's good enough. Okay. And the standard, I mean, one way of taking it is you can compactify S. You can sort of, I won't get into detail. So let S bar be a compactive, you embed S into some compact set S bar, then the continuous set of continuous functions on S bar is, has countable as set, and you take a collection from its unit ball or something. What's that? No, this is the, if this is true for all f, that's an equivalent definition of convergence in PS. Yeah. No, this is one of the definitions, in fact. I mean, there are some 5 different equivalent definitions. If integral f d mu n converges to integral f d mu infinity for all bounded continuous f, mu n converges to mu infinity.
No, I'm talking about mu n converging to mu infinity.
Yeah.
It's on the induced metric on P of s.
Yeah, yeah. So that this is one of the characterizations. Something called Portmanteau theorem, which gives some 6 equivalent conditions. This is one of them, most convenient to use. So all I'm doing is to replacing it by a countable set for so that you can apply it. Now this actually I think is better rated, but mu n, let me just say it in words. Mu n is a Markov chain, right? Just by from construction. From mu n you are generating mu n plus 1. It's a PS valued Markov chain. So now I know that it converges. Now just think of finite state Markov chain. It's best to go by analogy. You consider a finite state Markov chain. What you expect is that it will converge to some stationary distribution. If I say that actually Xn converges, that means it's going to an absorbing state. So what this says is that mu n is concentrating on some Dirac measure at a fixed probability measure, delta at gamma where gamma is fixed. So that explains the collapse. That's the claim. Okay. So shall I go to the next one unless there's some question?
So I just wanted to know, so when you say something is collapsing, what do you mean by that?
No, I am going the other way.
No, here the distribution collapsing.
Collapses to a Dirac. That's what I.
What does collapsing in the generative model mean?
No, there is the same thing. You get garbage in the end, so you start saying the same thing. There are sort of, it's maybe, I don't know if, yeah, I think I have one more slide, and that will say a little more. This is kind of vanilla collapse. Oh, sorry, I don't seem to have that, but anyway. What happens is that if you are not injecting fresh data at all, this is what you will get. If you are injecting fresh data, actually get not something as disastrous as this, but depending on how much data you are injecting, it will be basically a highly corrupted version of the data. So if you are just injecting small amounts, it will be mostly garbage with some semblance to. Okay, so this is something hopefully will be finished soon. So this is memorization diffusion model, is a similar phenomenon. So this is the what's called Einstein-Uhlenbeck process. The first thing is a linear stochastic differential equation. And if you flip it, you get that. So this is an old result, goes back to Falmer and others. And that grad log P is actually the P of x comma t is the probability density of the original process xt at time t. And so the reverse diffusion depends on the grad log of P of yt comma x0. Is that correct? Yeah, I think so. Yeah, and then you expect, because you are reversing the process, you expect that yt will have the distribution, same distribution as mu naught. Now you have, so the way you use it in generative models, that you have a bunch of images coming from mu naught. You just run a forward diffusion with that as the initial condition. You will get something. Take that as the initial condition for a reverse diffusion, and you expect to get more samples from the same distribution as mu naught. Okay. Now, the hard part is how to learn this, what's called the score function. And then this, most of the work is here actually, so I have just written one small para. So there's some mean square estimation based on, you just take the distribution, take the sample generated by the diffusion model and use it to estimate. And so this is where what they call memorization will kick in. What's happening is that it's like the case I previously mentioned, right? You are learning something about a model, you are plugging it in to the same model, taking the next example. It's kind of feeding on itself. So we have basically, this is oversimplified approach, but we'll hopefully finish writing this up soon. Basically, similar explanation for memorization phenomenon. And there's also, you can explain some other observed phenomena. So this depends on the noise level, as I said. If there's fresh data also being included, it heavily depends on the noise level, and people have made various observations that high noise levels, no memorization. That, if you know stochastic approximation, is obvious. And when a cautious the step size is large, there's more noise. That is also obvious. But anyway, like many things, these are getting rediscovered. Okay, so maybe I should slow down. I seem to have a lot more time left. I was a bit worried that I have too many things. So is there any question? Now this is fairly different from this time onwards, this is slide onwards. So this actually did not go well with ML, at least one ML journal, which didn't like it at all. So I am trying some control journal now. So what you have is the trying to explain okay, fact one, observed fact is that if you have a deep neural network with many layers, then you see that some modes either decay too fast or explode too fast, and you want to suppress that. And so you add one forward connection from for each layer, you take the input and add it to the output, and that dampens the whole thing. So that's the claim, and that's the observed fact. And there are the various works sort of trying to explain it at all. But I mean, whether you like this result or not, I think this is the correct framework at least. What you have is a composition of functions. I treat betas are the parameters. So if you want to look at how so what you are going to do is that, okay, let me go through the notation. Let me write down the Jacobian matrix. It will be a product of Jacobian matrices by chain rule. Incidentally, I should mention just as a complete digression. Physicists like to poke fun at, no physicist I hope, poke fun at electrical engineers or engineers in general. So a recent talk I attended on backpropagation, the speaker said that the computer scientist rediscovered the chain rule, called it backpropagation. Ho, 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 etc. All of them had a good laugh. The reality is that the guy who did that was a physicist and got a Nobel Prize eventually. Okay, so the way to add, so I want to look at the action of this on some initial vector. That's what one should be looking at. And this is a well-studied subject. It's not nothing I'm cooking up. It's called multiplicative ergodic theory, and something called multiplicative ergodic theorem for random matrices goes back to, I think, probably 60, 70, 80 maybe, I don't know. It's old enough by Oceladates in Russia. I will be using a different version. So so this, I think this is where the weakness of this result, that I am assuming the strong conditions because I am using one particular theorem of somebody else. So let mu be a probability distribution on this set, okay? So I'm imposing this restriction on it's stronger than being non-singular. In fact, yeah, it's quite strong. So, and let Xn be IID sequence in this class of matrices. So I'm taking this class of matrices. So basically, I will tell you where the problem comes. I'm considering a fixed dimension and multiple layers of nonlinearities from RD to RD, okay? The fixing it is not bad. You can put some dummy connections, etc., which contribute nothing. But assuming that if the dimension changes from layer to layer, but it is bounded by some common D, one can massage it. But the problem is that that won't ensure this kind of condition, non-singularity. So that's where the weakness is. But nevertheless, I think it gives some intuition why these things happen. So I'm taking a random sequence of matrices in this class. And then there's this multiple, oops, what about? Yeah, so this is a Furstenberg-Kiefer theorem. So this is 60s, and again, I am not an expert either. The multiplicative ergodic theory has come a long way, so there could be better ways of doing this also. So basically what they have, if you forget the jargon, look at this. So there are subspace, increasing subspaces, but what's more important is this differences in subspaces. Li/Li plus 1. So Li plus 1 is contained in Li. So basically the Euclidean space is kind of a direct sum of many subspaces. And I take this initial vector V in one of them, say this Li/Li plus 1. Then this multiplicative ergodic theorem tells that I think there's a 1 by n missing. Okay, this is even a bigger typo. This it should be limit n tend to infinity of 1 by n log. Okay, so exponential growth rate you are capturing or decay. There's a well-defined rate, and it's actually arranged in a decreasing. That's its notation, but you get a well-defined explosion or decay rate for the product of random matrices. Okay, and this is the part which Furstenberg-Kiefer did. They characterize. So you look at this object, and they characterize it as. I mean, this is their theorem basically. So this mu is what he chose. Nu ends up being sort of stationary distribution normalized for, it's actually unit vector, but you do go one step further actually. We are looking at eigenvectors, so you end up considering x and minus x as the same. So eventually I will start mentioning somewhere the projective space. So you have finitely many choices of nu there. Corresponding to the stationary distribution of a certain Markov chain, and this is the main result. So if A gets replaced by I plus A, that's the residual connection, one forward connection equal to identity, then the normalized, that should be nu, actually, so another type of news that you get will correspond to eigenvalues that are a smaller perturbation of unity in the projective space. What it means is the increase or decay of blowing up or decay of eigenvalue is suppressed in a quantifiable way. So as the number of layers become large. Now what's the problem, as I said, is the strong assumption. That Furstenberg-Kiefer, I assume that integral of log plus matrix norm A plus log plus matrix norm A minus A inverse mu dA is finite. In general, they may not even be non-singular. Yeah, and it's fairly strong. See, as I said, the multiplicative ergodic theory has come a long way, and I don't know whether there are improvements of it.
Isn't that integrand just the log of the condition number? Because norm A into norm A inverse is the condition number. So it's just the log of the condition number.
Yeah.
It's always going to be non-negative. So the point is that it does not blow up too fast? I don't
No,
think.
no. It may not be invertible in the first place. So what the way I fix the dimension is that assuming that, so the neural network, the dimensions are not fixed, they will be changed layer by layer. I assume there's an upper bound and assume that treat it as a map from RD to RD at each layer. Now for some layers which are actually are less than D variables, I'll have to massage it by adding some dummy things. That will make it singular. I'm wondering if one can use some kind of genericity argument, but I was not able to do that. So,
Yeah.
non-singular matrices are generic. But that should be, that's not enough. You have to justify more. Why it will still give a reasonable result, even in the singular case.
Can you just go to that assumption? I'm a bit confused about that assumption. So this integral is over all A that is sampled from the distribution mu.
Yeah, so mu is fixed.
So mu is fixed. So, but the set M is also consisting of all such A's. So that is not clear to me.
Yeah, all A for which the average of log, log of the conditional number.
But here you are sampling A randomly, right? That's how the integral looks like. You are sampling A according to the measure mu. Is that correct?
Yeah.
So then A is to be treated as a random variable here, and there you are saying you collect.
Yeah.
all
So
such
no,
A's.
this is just the definition. So I mean, this is not. Yeah, that's true. I mean, this
So
is the
calligraphic M a collection of mu's, or is calligraphic
correction of A's.
A's? Okay.
Mu is fixed.
But this integral is over all A's generated from mu, right? The
Yeah,
integral
that's what
is-
I'm going to. Yeah. So I am generating A's from mu subsequently.
So
for
the confusion
applying.
is that in this integral there is no single A, right? There is like A's that are generated
Yeah.
using me. So I think there is some notational.
No, this is fine.
discrepancy what I
So
see.
the M is the set of A's so that this integral is finite.
Okay.
Like we are essentially integrating over the space of A's right here.
Yeah, mu. So
Yeah,
mu of
so-
dA.
So we want to sample
Yeah, that's true.
A,
Circular.
but-
Yeah, that's true.
Yeah.
Yeah.
So we want to sample A,
Hmm.
but we are integrating over all the A's.
No, but there's no problem defining this object. So suppose I take A and suppose I'm given an A, I check if this integral is finite. If yes, I put it in M.
But if you fix A, what is mu d?
Huh? No, okay, maybe I should have changed notation. Yeah. Call that A prime inside the integral. No? Hmm?
As I said earlier, once you fix A,
Hmm?
that integrand is just the log of the condition number.
Yeah, yeah.
Okay. So mu is fixed, and if you are integrating over all possible A's,
Oh, okay, okay. Yeah, now I see. Yeah.
then what is
Yeah, I
A
should
doing
have-
on the outside?
Yeah. Yeah, you're right. Yeah, I should have probably should get rid of this, I guess. So basically, okay, maybe what I should say is the support of mu. What should I say? I want this to be bounded. That's also right. Collection. I want to sample A according to mu. Such that this inequality holds. Yeah, that would be the better way. Not define M at all. See, basically, I want to sample A with mu and insist on this condition to be true. That's what it amounts to. Okay.
If you sample A from mu, then I guess A can be generically non-singular, right? Because
Yeah, but I don't want them. You see.
Non-singular matrix has a finite condition. That's what I was trying to say. The integrand being finite is not a big deal. Generically, it's always true. I don't get what you
No, but if I suppose I consider a distribution where, say, the condition number approaches infinity while being finite, and mu is such that you put. See, for example, if I say I want to consider, I have a mu and I want to consider random say sample some xn such that expected value of mod xn is finite. Roughly, that's the counterpart. I think it's worded badly. So I want to prove law of large numbers.
I'm beginning to suspect that you want mu, maybe on the outside, left to the left of the integral, is it the set of all measures, mu, and not
No,
the set
that's-
of matrices, A?
Just see, basically, yeah. No, it's not definitely not the set of measures. So what I am going to do is just sample according xn IID with law mu. That's all I need. And for the theorem to be true, that integral needs to be finite.
What are we sampling?
Sampling matrices with a distribution mu. So just I think it's just let me go back to analogy with law of large numbers. I'm sampling x1, x2, xn, etc. And to say that sum of xi from 1 to n by n goes to its mean, all I need is expected value of mod xi is finite. So that's kind of situation. I need for this statement to be true, I need that expected value of that log conditional number should be finite. I think I should put it that way.
Professor Borkar.
No. Yeah, the set depends on mu, yeah. Yeah. Yeah, the m depends on mu, that's true. I think I'll get rid of this. That's the best thing, you know. Yeah. Okay. Yeah. Yeah. No, mu is fixed. I'm sampling from a fixed measure. Yeah. And I pick one mu from there. Yeah, okay, maybe. Yeah, okay. Yeah.
measure such that this
Yeah,
integral
yeah,
is
yeah.
finite, and then having chosen
Yeah, then sample from there.
from
Yeah,
that set, we generate matrices according to that law. That
yeah,
makes
that's
sense.
correct. Yeah.
But so that A is basically not a set of all measures.
Yeah, so I will change the definition. I think it's not an excuse, but I had somehow adapted the things straight from that paper and probably was not careful enough.
Professor Borkar, here.
Who? Oh.
Hi. Sorry, I couldn't understand the conversation. So is it like M the largest set for which this integral is finite? Is that
No, what he's suggesting is that define mu. So maybe take some, say, consider, say, all non-singular matrices. Consider set of mu's for which this statement is true and pick one mu from there. That's the correct thing. Yeah. So what I should have said, M is the set of mu such that if you integrate matrices with respect to that, this thing is true. And yeah, and then pick a mu from there. Yeah. Yeah, so that was the claim is that you can show that, and because you're looking at eigenvectors here, you go to projective space because x minus x is same, x times alpha x is same, and so on. And then it's I plus a is closer to I than a in that space. Yes, I mean, it's intuitively obvious. To some extent, the physicist was right. I mean, even he poo-pooed this as well. I mean, he poo-pooed, spent some valuable lecturing time making fun of computer scientists. So this was one of them. Okay, so this is something older. And this I am not going into details at all. So there's something called Shapley-Folkman star lemma in mathematical economics. So first define the Minkowski sum of two sets. So B, that whatever it is called, B sum C, B plus C, let's say, is the set, B and C are sets. So B plus C is the set of X plus Y. Oops, why does this happen? X is in A and Y is in B. And suppose I keep taking Minkowski sum of A with itself n times. So A n is A plus A n times. Then the Shapley-Folkman star lemma says that A n by n converges in Hausdorff metric to convex closure of A, closed convex hull of A. Okay. And this actually some interesting story. Shapley-Folkman never published it. So the star was a young economist trying to do something, and he asked them whether for help, and then they sent him this theorem, which has become well known now, but it was never published. And the star then improved it a bit for its purposes and so on, and it was called Shapley-Folkman star theorem. So basically game theory people from economics. And now I want to apply that to something called epigraph. So epigraph, if you do a sort of reasonably advanced level of optimization course, you will see it anyway. So epigraph of function f is the set of pairs x comma y. So f is a function on some domain D. Then epigraph of f is pairs x comma y, so that x is a D and y is greater than or equal to fx. Okay. So I take D to be nice close bounded convex, etc. And let f sub star be the, let's say f star is the convex minorant of f. That means the largest convex function dominated by f. No. I'm just applying Shapley-Folkman star. I mean, is it known all? Oh, okay. But is it known as Shapley-Folkman star, or I found it from?
I'm saying that the convergence of an divided by n to the epigraph of the convex envelope, that pretty well established. But your interpretation in terms of this making the training problem easier, I think that is new. I mean, I don't think this particular equation, bottom equation cannot be claimed as new.
No, I'm not. See, the thing is, it's just a corollary. It's immediate. It's nothing to prove.
Yes.
So, is this known as a corollary Shapley-Folkman star? Is my question. Or did other communities probably independently found it? That's possible. Yeah. So this I have not given any details of it, and that basically you can sort of argue with this as a starting point that because of this kind of asymptotic convexity, see, okay, again this is trying to explain yet another phenomenon that shallow and wide networks do well. Why? I mean, this, of course, this is this is actually arithmetic mean, it's not arbitrary weights. But then you can invoke a Tauberian kind of theorem. So if exponentially weights, or I mean, it's not any weights, but you have to have the property that if you have width n and you use weight a sub n comma I going from say minus n to n, then what you need is that the sum of these weights is 1, and for each n, and as n goes to infinity, they should basically averages with respect to this to start approaching Cesaro averages. So the Tauberian theorem does that for exponentially weighted, that people in control know, and this limit of discounted cost is average cost and so on. So that's the, and it's not true for arbitrary a sub ni, even if they're positive and sum to 1, it need not be true. You can easily go up counterexample. Okay, so this is not entirely the last slide, but want to thank thank my funding agency, Google Research. I think Dheeraj is here somewhere. Ah, there. Okay. And this is the original, in case you're wondering where I got that verse from a film called Sound of Music, which was a major hit long time back. What?
I'm saying that for people like you and me, we should add, so somewhere in my youth or childhood or old age.
Yeah. No, in fact, the people, only those who are reasonably senior will know about this film. Okay, so any more questions?
Yeah, we have quite a bit of time for questions. Any questions?
Can you go back to that grokking phenomena that you were talking about?
Essentially, I should mention that those are sort of idealized figures. Actual graphs, you look at the paper, they look quite ugly.
No, in that result of yours, where you said that when in the medium range, when the time scales overlap.
So that I don't analyze. I just sort of.
No, but what do you mean by middle range? And even if they become comparable, what is your claim? Like,
no, then you cannot say make either of these. See, in first and last stage, one of the variables dominates.
yes.
In first one, the slow variable is quasi-static, and fast variable will quickly come to close to minimum, minimizer. And in the final stage, basically, the fast variable is tracking the slow variable, and is essentially the descent for the slow variable. But it's in between the range, you cannot say one will dominate the other, because those arguments are based on one gradient becoming significantly larger than the other.
So if you don't mind, can you go to the figures as well? Yeah, so for example, in this steep descent, so is this the tail behavior or the middle behavior? The steep descent that you see in the validation error.
No, no. Which one?
The green curve steeply falling down.
Yeah, that's the. Oops. So this things may not be as pretty as this that to do it. So initial thing is corresponds to X rapidly converging to Y dependent minimizer. Then there's this confusing thing, and then the Y takes over.
So are you saying the tail behavior is why?
Yeah.
I mean, what explains the final descent?
Yeah.
I see.
Which may or may not be desirable.
And can you explain similarly the catapult phenomena? Like why?
No, that's just, I think it's just a repeated thing. So my way of thinking about it, if you see, I took two scales. There could be more than two. In fact, there could be continuums. It's an extremely stylized model.
I see.
So suppose there are 3 scales, you may see 2 such things.
I see. Thank you. Thank you.
To apply the result of stochastic approximation in the 2 time scales, won't you need the step sizes to go as an by bn goes to 0? Here the step sizes, the ratio would be 1 by epsilon.
No. I'm working with constant step size, which is what ML people do. So this decreasing step size gives nice, clean results.
Yeah,
it will
so
give
yes.
almost sure and everything. So I am fudging a lot here. You don't get almost sure convergence. You will get concentration around the point.
Okay, sure.
I think.
Thanks. Thank you for the talk. I have a few. So if we now bring it to the context of RL, I'm talking about the grokking problem as well. What can you comment about your X and Y, the faster and the slower variables?
Again, see, the thing is, the model you are fitting, there are some, I mean, it depends mostly on some and not on others. Incidentally, I should mention that decomposition may not be unique either. Okay, so I comment on that in the paper that it may emerge. It depends on what you start with and what initial data you get. You may finally lock onto one of the various. There's nothing where no variable may come branded as strong or weak. The algorithm may classify them as strong or weak as part of the training, and then on this will be true.
Right. So as a follow-up to that, I'm wondering if the theory passes on without any extra, how do I put it, assumptions to RL, because
I haven't thought about it yet, but my hope is that it will. Okay. Otherwise, I won't have ventured talking about it in Google's conference.
Right. So there, at least the initial data plays a lesser role as opposed to, in some sense, the ergodic occupation.
Initial data is not at all a trivial thing. See, for example, if you have a multimodal kind of initial, you may get locked onto one mode, depending on the very start.
Right. So sometimes they also call it as loss peaking, right? This phenomenon where your loss peaks towards the end or in the middle, and it happens constantly. When I don't know, that's the terminology I'm aware of. Given your theory, is there a way out of, because this is in some sense where practitioners stop and say, okay, I'm not going to use this model now.
No, but this is, yeah, okay. So see, if it's of course there are too many parameters influencing this, but if at least according to Austin et al. Results, if it's a very high dimensional function of many variables, and you put some strong Lipschitz constant, that forces it. It cannot depend heavily on all the variables equally. I mean, this Austin makes it precise, but
so Lipschitz on the gradient, or
yeah.
So that would be in
no, sorry, Lipschitz on the function.
On the function itself.
Yeah.
Okay, interesting. Maybe there are others.
See, the way I view it, I said it a couple of times, that Lipschitz constant, for Lipschitz, then it's almost everywhere differentiable, and the Lipschitz constant will be equal to essential supremum of non-gradient. Okay. Now, if that cannot be very high, sorry, that cannot be bounded by a fixed number with all its components being very high. Now, that differs from Tim Austin's result is that he actually says that there's a separation, that some it could be some kind of continual tapering, etc. But he says that there's a separation between heavy dependence and low dependence. With high, there's all high probability and all that. All the claims are probabilistic. So he actually proved non-concentration. His paper is called what absence of, I forget what it's called, something no concentration in infinity ball. Huh? No. Let's see.
Do you mean anti-concentration? He used to work on anti-concentration.
He just showed that it doesn't, this paper shows that it does not concentrate. Failure of concentration, but there he's talking of probability measures.
Understood.
And he uses this problematic situation in function space to show that they cannot concentrate in. This actually proves that step towards proving that the probability measures don't concentrate.
Got it. Thanks. Because we are also studying a similar problem, and there we are observing that decaying learning rate, probably not every step, is the way to go to control the Lipschitz constant of the gradient. Because if you think about deep learning, there may be a Lipschitz constant if we choose, C infinity activations. But that Lipschitz constant will grow and will grow exponentially. So it will be locally Lipschitz continuous. I'm talking about the gradients. Right? And there the data itself will not play that much of a role in the Lipschitz constant if we carefully choose activations, meaning the magnitude of the data. Because there's also this theory related to loss peaking and or like you're saying grokking, and whether the data itself is having compact support or infinite support. Maybe we can take it offline.
Okay, I think this the most problematic part of my talk, which was the multiplicative algorithmic theory, it was that attempt to address this kind of issue.
Right. That was also one of my questions. It's like, how are these two linked?
But I think this is a natural way to look at it.
Okay.
Because that's the classical math way to look at it, composition of functions, random maps.
Thank you.
Incidentally, multiplicative algorithmic theory has been used in machine learning to do something else. I Googled hard for it and found some references, but he kind of interprets, I think, some application to biology or something using this. And it's, I have that reference somewhere, I don't remember it offhand. It's not that it is the first use, but I think this is a natural use to look at this phenomenon. You're composing a large number of functions. Yeah, Austin.
So can you go to that discussion where you said that the measure collapses and so on? I think you were talking about in the generative model setting, right?
Yeah.
So I wanted to ask, so there is this phenomenon of performance collapse in reinforcement learning as well. So do you conjecture that maybe what you are explaining here could perhaps be the reason there? If that is the case, I wanted to know, is there some way to prevent this performance collapse? And do you think that injecting new data is one of the reasonable ways, or one has to do more sophisticated?
I don't know this phenomenon.
I see.
So you have to make one kind of claim or disclaimer. Like the Beatles say, I depend on the help of my friends. To get the problems, I depend on people who are mainstream ML. I jump from topic to topic. So you tell me this, I will start working on it.
Thank you.
Yeah.
The question is at what rate?
Oh, okay.
So it's desirable that it grows.
Yeah.
In the RL setup. Now that I have the mic, if you don't mind, one more question. Just to sort of connect your grokking to the last result. Again, I feel like the last result is in some sense a solution to the original problem, to sort of the grokking problem. Can you comment on that, or am I way off?
No, last the convexification.
Convexification.
No, but that you go horizontally. You know, I thought hard about it. I couldn't fit the deep neural network into the convexification thing. I mean, it may be possible, but I couldn't do it.
Right.
It's compulsion of function, whereas this is just a weighted sum.
Right. Even when I try to prove the results, it's easier for the shallower networks. But somehow, empirically, the deeper networks also sort of have similar. I mean, they give you similar results. So, but yeah. I'm just checking if there's something else I wanted to ask. Yeah, for the collapse problem, no? Sure that it converges to a Dirac measure, but what can you tell about the point itself?
No, it's a random Dirac. I mean, it's delta at gamma. Gamma is random.
What can you tell about gamma? Can you say something qualitative for learning? You said it's garbage, but is there like a map?
I think you will have to specialize these things to specific problems to say more.
Okay.
That's my feeling, because this is too general. I mean.
Right. This is typically done in vision, right? You use some ResNet and you keep running it. Sorry, that whatever deep latent model, and you keep running it forever. And the output of such models is typically parameters to a Gaussian distribution. So I was thinking maybe you could say something about those parameters.
Again, you'll have to tell me about the literature.
Okay, yeah, sounds good. Thanks.
Hi, Professor Borkar. I had a question on your memorization in diffusion slides. So how many diffusion models are getting trained here? What is the setup?
No, just one diffusion model.
Just one diffusion
naive
model.
classical and nothing fancy.
So where is collapse? So you had a comment about collapse in your
No,
slide.
it's what I'm saying is the memorization is a similar phenomenon.
Okay.
You kind of, because you are feeding on yourself, it's like just like the original collapse model. It's just feeding on itself, so that tends to, that's not good.
Okay.
Unless there's some fresh injection of data all the time.
Yes. I'll take
These
the
things are
remaining
inevitable.
questions
That's rough intuition.
Okay. Thank you.
Okay, so in the interest of time, we'll stop here, and let's thank Professor Borkar. Yeah, and here is a small token of appreciation. Thank you. We'll now move to our next speaker, and he is Professor Vidyasagar himself. So while he reaches the stage, let me just read out. Okay, so Professor Vidyasagar received his BS, MS and PhD degrees all in electrical engineering from University of Wisconsin at Madison. His PhD was in 1969, and then for nearly 20 years he was at Marquette University and then Concordia University, University of Waterloo. And in '89 he returned to CARE, where he was heading this CARE center in Bengaluru. And then he moved to Tata Consultancy Services in 2000, and then 2009 he retired from TCS and then joined the University of Texas at Dallas as a professor. So he is extremely well recognized. He moves across areas. Now he is more interested in reinforcement learning and stochastic approximation over the last 10 years maybe. And
Stochastic approximation? More like about 5, I guess.
Okay. Yeah, so he's also written a book. Your book has appeared already on reinforcement learning.
I hope it will be published by Springer.
Okay. Yeah, so he's extremely well accomplished. He is also a fellow of the Royal Society, amongst the various distinctions that he holds. So without much ado, may I request you to...
Okay, before I start, when I was listening to Professor Borkar, I found that sound was very, very indistinct. Did others find that? Okay. So I'm going to try to stand as still as possible and just talk from here. Now, thank you, fella, for the long introduction. You could have summarized into one sentence. Professor Vidyasagar is really, really old. Okay. So, this is something I've been working on for the last few years, last few months, I mean to say. And can you hand me my cell phone? I just like to have the timer. Yeah. I'll just use the timer. Okay. Are you using this? No, I don't want that. Thank you. Yeah, thank you very much. So as I said, I've been working on this specific problem for the past few months, and the talk is based on this paper called Convergence, with the same title of my talk, and it's going to appear in this journal called Pure and Applied Functional Analysis. Slightly bizarre place for a paper on stochastic approximation, but it's a special issue in honor of Professor Alain Bensoussan. And at the end of the talk, I'm going to give a bibliography of earlier papers that are the predecessors of this paper. Okay? So here's the outline. Let's start with the problem. This is a standard problem. You are given a continuous function j. Thank you very much. And you want to find a global minimizer. So now the way I use the terminology is global minimum is the value of j, and global minimizer is the value of the argument that achieves the minimum, right? I try to be consistent. I think I'm consistent most of the time. So I'm going to make two assumptions. First is that three assumptions really. The gradient is globally ellipsis continuous. The infimum is not minus infinity. It's finite. And it is actually attained. So the set of minimizers rather, is non-empty. So let me remind you, I'm sure most of you know this already, but let me remind you of some standard algorithms. Everybody's workhorse is stochastic gradient descent. You start with some initial guess theta 0, and then at iteration t, there is a thing h of t plus 1, which is called the stochastic gradient, and it's roughly equal to the gradient. Then you take a step in the negative gradient direction, and alpha t is called the step size, and you repeat. Now, the phrase momentum-based methods refers to algorithms where the search direction at step t depends not only on the current theta of t, but also on the previous one. And the stochastic heavy ball and stochastic Nesterov accelerated gradient methods, they are the best known momentum-based methods. Now, you may say, why should you only look at the current theta and the previous theta minus 1? Why not have a memory of t steps? Theta, theta t minus 1. You can call this multi-step momentum method. As far as I know, nobody has even looked at this. Now, it could be because there is no advantage to it, or nobody ever thought of this problem. And if some of you are interested, you can examine this. Okay? So the stochastic heavy ball algorithm says theta t plus 1 is theta t minus that is just the stochastic gradient descent, plus this extra term, mu t into theta t minus 1. Mu is called the momentum parameter, so you are pushing it in the direction in which it is going already from the previous step. And this h is a random approximation to the gradient. And this mu is called the momentum parameter. So if the h is actually the true gradient and the momentum term is held a constant, and this is called the heavy ball method. So the point is there is no stochastic here, just heavy ball. And this was introduced by Boris Polyak all the way back in 1964. It's a long time ago. And here I'm going to allow H to be a random vector. Now, then there is this thing called Nesterov's accelerated gradient method. And this was proposed by Yuri Nesterov in 1983 in a paper that was in Russian. So far as I'm aware, there is no English translation of that paper word for word. People have built on that, but I've been looking for an original translation, I haven't found it. Now, the way he wrote it was very opaque and almost mystical, you can say. But then in 2013, Sutskever and company, yes, that's the same Sutskever who is now a multi-billionaire or whatever. So he rewrote Nesterov's algorithm in this fashion. He said, theta t plus 1 is theta t plus this momentum term minus alpha t times the gradient. So what's the difference? The difference is that ht plus 1 is a random approximation of the gradient, not at the current iteration theta t, but the current iteration plus this correction term mu. So essentially with Sutskever's reformulation, in heavy ball, first you compute the gradient and then add the momentum term. And in Nesterov, first you add the momentum term and then compute the gradient. So this made things really, really clear. Before that was not clear at all. Also there is an important change, is that if you look at the heavy ball, the momentum term is usually kept constant. But the step size goes to 0 if you want convergence. If you have the step size not going to 0, what will happen is that the iterations will converge to some neighborhood of the answer, but that's all. If you want it to actually converge to the very value, then the step size has to go to 0. What in Nesterov is the opposite. The step size is usually kept constant, and the momentum term approaches 1 from below. Okay, now, I'm going to give you a unified formulation. And I did find one paper that has something similar to this. I cannot claim complete originality, but I think it's reasonably original. The analysis, of course, is my own. So in this case, you see, I don't have one updating formula. I have two updating formulas. So I have two vectors, W and V. They have the same dimension as theta, the parameter of optimization. So Wt plus 1 equals Wt plus something something, Vt plus 1 equals something something. So what do you notice? There is a V in that equation, but there is no W in this equation. That's kind of a triangular structure. Okay? So that's the key, as it turns out. Now, what is H then? It's a random approximation to the gradient at Wt. So Wt is that one. So at step t, you calculate a vector H which is roughly equal to the gradient of J at Wt. And you have all these constants. You have At, Bt, are sort of constant that are deterministic. And then alpha t, that thing, is called the step size. Sorry, that's not it. Alpha t is the step size. So now, if you look at these equations, the same step size is there in both equations, except that in the V equation, there's just the step size, whereas in the W equation, the step size is multiplied by yet another constant. Okay. Now, you may say, all this is very fine, but I don't care about all these things. I want to know the original variable of optimization. So how do I get it back? So you just take it as theta t plus epsilon t Vt, and so you can recover theta. Now you just look at this formula. If I can show that W converges to a minimizer and V converges to 0, then assume you can follow that theta converges to the minimizer, right? But it's easier to do all the analysis in terms of these two variables
W and V alone. Now, stochastic gradient descent, heavy ball, snag, they are all special cases. And don't waste too much time reading this paper, this slide. So if I put this choice, I get stochastic heavy ball. If I put mu equal to 0, I get gradient descent. And if I choose this choice, I get Nesterov's method. And there is a slight wrinkle here. I won't dwell on this too much. This constant depends not just on the current momentum term, but the next momentum term as well. Okay. So for my paper, it doesn't cause any difficulties, but in other cases it can. Anyway, so what are the classes of objective functions I'm studying? So I'm going to introduce something called invex functions. How many people have heard of invex functions? I know few would have heard, but how many have heard of it? Can I have a show of hands? One person in the front row. Okay, well, that's somewhat less than what I expected. So what was the motivation? So why is convex optimization easy? Let's ask ourselves that. So the reason why convex optimization is easy is because of this inequality. If you take two arguments, phi and theta, j of phi is bounded below by j of theta plus the inner product of the gradient at theta and times phi minus theta. So if you take a convex function, extrapolate linearly, the true curve is always above the linear extrapolation. So in particular, if the gradient is 0, then this term disappears. So if the gradient is 0 at some theta star, then it means j of phi is greater than or equal to j of theta star, so theta star is a global minimizer. So this person called Hansen in 1981, he proposed a new class of functions which have similar properties. And this is not directly related to my paper at all. But I'm going to introduce them to you because I think it's potentially a fun area of research for people who are looking for a topic. So he introduced functions that need not be convex but still have a similar property. So Hansen's definition is a smooth function is invex if there is a function eta such that j of phi is greater than or equal to j of theta plus the inner product of this eta function multiplying the gradient at j of theta. So just go back one. So if you just choose the function eta to be phi minus theta, this inequality holds. Okay. So this is all right, and it's kind of obvious that if j of theta is 0, then j of phi is greater than or equal to j of theta. So the property that a stationary point is a global minimum is obvious from this definition. But the really interesting result in this area came in 1985 by two people called Craven and Glover, and they proved the opposite, which is, suppose j is a smooth function, and it has the property that every stationary point is a global minimum. Then there exists a function eta such that this is true. Okay. So now this theta, yeah.
So when you say stationary point, do you mean grad j theta star is 0 or j theta star is 0?
I'm sorry. Do I mean what?
On the left, you said.
Oh, here, yeah, it's a type. That's a typo. Okay. It's grad. Yeah, thank you. Gradient of j is 0. I mean exactly this. That's what should have been on the next slide as well. Yeah, sorry about that. Yeah, so if the gradient is 0, then it's a global minimum. So these guys, Craven and Glover, proved the opposite, namely that if it has this property, that every stationary point is a global minimum, then there exists a function eta such that this inequality is true. Okay. So as I said, this has nothing to do with my paper, but there are a lot of students here. So I want to throw out one idea I had. I said, okay, suppose I give you a function eta and say my objective function j satisfies this inequality you find a global minimum. So what would you do? Kind of obvious. You take gradient descent, except instead of descending in the direction of the gradient, you descend in something along these lines. What's wrong with that approach? What's wrong with that approach is that it doesn't survive noise. So if you get not eta, but some version of eta, then theory collapses totally. So this is a very cute result, but it's not directly useful. So I introduced two new classes of invex functions. One is called PL. PL stands for Polyak and Lozachevich. Okay? Now, what's the point here? I've already assumed that J has a Lipschitz continuous gradient. And one of the consequences is this inequality. So if the function has a gradient with Lipschitz constant L, then you know that the function cannot grow more than quadratically. But this is not saying that. What it is saying is that any point, so slope is no larger than 2L times the value of the function. Okay? That's a very useful result. So a Polyak-Lozachevich function is one for which the same inequality holds, but in the opposite direction. And there is a constant k such that the norm of j theta squared is greater than or equal to k times j theta. Now again you can see that if I normalize the, by the way, I'm assuming that j star is 0. So if I look at this function, if the gradient of j at theta is 0, then that means j at theta is also less than or equal to 0. But j of theta can only be non-negative. So this is definitely an invex function, right? Just one second. I barely hear you.
Sorry for asking this, but what is J star again?
J star is the minimum.
Oh, okay, sure.
See, if I don't put the minimum equal to 0, then instead of j of theta, I'll have j of theta minus j star.
Sure.
Any other questions? Okay. So here's a simple example of a non-convex function of class PL. So suppose this is a one-dimensional example, and you can make multi-dimensional versions if you feel like. So suppose you just take a plain old quadratic and add to it 3 sine squared theta. Then what happens is the function is this curve, and you can see all these wiggles. So the function is clearly not convex, right? And then if you plot the gradient squared divided by the function itself, it comes down, but it doesn't quite touch 0. You can't see it from this picture, but this satisfies the PL condition with k is equal to 0.3511. And so that is the secret behind this number 3. Why 3 and not 2 or 4 or something? If you make it 2, it's still a PL function, and this number becomes higher. If you make it 4, the function is no longer PL because it actually comes down and touches the axis. This is a simple MATLAB experimentation. Okay. So now I want to talk about the next class of functions called KL, and for that I need to introduce a concept called class B. A function phi belongs to this class B if it starts at 0, and for any real number epsilon, which is positive, and m, I should actually have added m less than infinity, it's finite, the infimum is always positive. So it means it starts at 0. It can go to 0 as theta goes to infinity, as the argument goes to infinity, but in between it is bounded away from 0. So here is this function. Phi is equal to theta, linear, then decaying. So what does it look like? It looks like this. So at 0, it is 0. It goes to 0 as the argument goes to infinity, but in between it's never actually 0. And in fact, if the function doesn't even have to be continuous for this definition to apply. So now I define this class, which I call KL prime. So K stands for Kudryka-Losachevich, is the same guy as before, but the inequality that the function needs to satisfy is the norm of the gradient is bounded below by some function of j of class B. Now if you just go back a few slides, so what this says is you can say norm of the gradient is greater than or equal to some constant times square root of j. Okay? Now square root of j is obviously a monotonic function. And the improvement here is that this function doesn't have to be monotonic. In fact, it can even go to 0 as you get farther and farther from 0. Okay? And why do I put a prime? Because this is not quite the original definition of Kudryka. What I did was to change his definition to a function of class B, but it isn't much different, so I just call it KL prime. Okay, so are you clear about the two classes of function? PL is where basically the gradient is bounded below by the square root of j, and KL prime is where the gradient is bounded below by some function of class B of j. Okay, and I just gave an example. It's just the same function, except I added something that go to 0, so that eventually, if I continue this graph long enough, it will come down to 0. Okay, that's small detail. Okay, so why are these classes important for this talk? So PL implies KL prime, which implies convexity. So every stationary point is a global minimum. And both classes contain non-convex functions, as I think I've shown you. Okay. Okay. So for my talk, the significance is if I assume that the objective function belongs to class KL prime, I can give conditions for the convergence of my unified algorithm, but no information on the rate of convergence. But if it is of class PL, not only can I get the convergence condition, but also the rate at which it converges. Okay. So finally we come to the convergence theorems. So let me begin with a few preliminaries. So I just want to introduce the concept of a filtration. Just out of curiosity, how many people know what a filtration is? Can I have a show of hands? About 10%. That's still pretty low. All right. So here's the idea. So every random variable is defined on some underlying probability space. Sorry for the missing parenthesis. So you have some set omega, some sigma algebra of subsets, and a probability measure, P. So basically a filtration is just an increasing sequence of sigma algebras. So that means Ft, there will be some F0 back here somewhere, and Ft is a subalgebra of Ft plus 1, which in turn is a subalgebra of F. So this is called a filtration. And if x1 and xm are random variables, and I see the same typo here, then the sigma algebra generated by them is a smaller sigma algebra such that each of these random variables is measurable with respect to that. Okay? So why do I define this concept? If I add one more xm plus 1, then the sigma algebra generated by x1 through xm plus 1 has to be bigger than or equal to the one generated by x1 through xm. So that just keeps growing, and it's a filtration. And this notion of conditional expectation is a little bit tricky, but if you have an RD valued random variable, and if you have some subalgebra of F, not Ft, sorry, Then the conditional expectation of x, well, okay, the actual definition of conditional expectation is really messy. If you assume only that the random variable is absolutely integrable. But if you assume that it is square integrable, the definition becomes very easy. It's just the best possible approximation to this random variable with respect to functions that are measurable with respect to ft. And best possible in what sense? In sense of the Euclidean norm. Okay? So I'm going to use this symbol et of x to mean the conditional expectation of a random variable with respect to a filtration, f of t. So once you have this et, you can talk about the conditional variance. Now if you have a plain old random variable, what is the conditional variance? It's the expected value of the random variable minus the mean squared, right? It's the same thing, except that what you subtract is the conditional expectation of x. See, what you have to remember on this slide, the key point is, if I have a random variable x, its expected value is a number, but the expectation is a random variable. That, to my mind, is one of the worst notations in probability theory. But unfortunately, nobody can do anything about it. It's very well entrenched. Okay? So when I say et of x, this is actually a random variable. But you can take this random variable, norm squared, take the expected value. Now this is just a plain old number. That's called the conditional variance. Okay. Now, my emphasis in this talk is going to be on almost sure convergence. So almost sure convergence is not a concept that lends itself to talking about rates. So here's one way of doing it. Suppose you have a stochastic process and ft is a sequence of positive numbers, not random variables, that's plain old numbers. So if yt over f of t is bounded almost surely, we call it capital O of ft. And if y is always positive and ft over y is bounded almost surely, then y is omega of ft. And yt is theta if it is both capital O and omega. And this is the most important thing for us. Yt is small o of ft if the ratio yt over f converges to 0 almost surely as t goes to infinity. So this is how I get around the problem of what do you mean by rate of convergence in the almost sure sense. Okay. All right. So let me list out the various assumptions. Remember that the iterative algorithm is defined in terms of these two auxiliary variables w and v. And theta is connected to these auxiliary variables through this formula. And h of t plus 1 is a stochastic gradient, meaning a random approximation to the gradient of the objective function at w. So this is the most important slide. What do I assume about the stochastic gradient? So first thing I do, I look at f of t to be the sigma algebra generated by all the past iterations and all the past stochastic gradients. The reason why h starts at 1 and not 0 is because there is no h0. Okay? So the assumption here is, okay, we need this quantity. Take the conditional expectation of the stochastic gradient at time t plus 1. I said it is approximately equal to the gradient at wt. So xt is just the difference between this quantity and that quantity. So this is what you would call the bias of the stochastic gradient. If you had an unbiased estimate, z would be 0. X would be 0. And z bar is ht plus 1 minus z. So because z is already the conditional expectation, z bar, it has a conditional expectation of 0. Therefore, the variance of z bar is in fact the conditional variance of h. Okay. So my assumptions are the norm of x is bounded by some constant times 1 plus gradient of j, and the conditional expectation of z bar, which is that thing, is bounded by some constant squared into 1 plus j. Okay, now you can say why 1 plus j? Why can't you have two separate constants, m1, m2? It doesn't matter. You can just combine them into one. Okay. Now, this is a paper by Rajiv Karandikar and myself in the Journal of Optimization Theory and Application, published last year, 2 years ago now. And these are the most general conditions under which anybody has proved convergence. Okay. This is what I said earlier. X is the bias, and this is the conditional variance. Most papers in the literature assume that your stochastic gradient is an unbiased estimate of the true gradient. But that is actually quite restrictive. For example, when you use this so-called zeroth order method, and they also assume that the conditional variance is bounded by some absolute constant that doesn't depend on the iteration number. But now when you use the so-called zeroth order method, where you compute h using only two function evaluations. So this is the way in which it goes. You take the so-called Rademacher vectors, and there are other ways of doing this, but this is good enough for now. So Rademacher vectors are random variables that are either +1 or -1 with equal probability, and they are independent. Each component is independent of every other component. So what you do is you take J and perturb it in the positive direction by some random d-dimensional Rademacher vector, and then you perturb it in the negative direction by the same random vector, and you allow for the possibility that while measuring this J, there is some additive noise here and there. Okay. Then you take the difference and divide by the ith component of the Rademacher vector. So what is the meaning of all this complicated formula? You get an approximation to the gradient at this vector, because what you've done is perturbed it by +1 times Ct, -1 by Ct, and divided by 2 Ct. Okay. Now, what do you notice about this? Well, and this is known for decades actually. This quantity is biased. B of t, which is this thing here, the magnitude of the bias, it reduces, this quantity is Ct, I call it the increment. You want to make it smaller and smaller. The B goes to 0 as C goes to 0, but the bad news is, because you're dividing by the C, see now there is this noise, and there's that noise, and you are dividing by Ct. So obviously the conditional variance is going to blow up like 1 over Ct squared, right? So what is the good news and the bad news? Good news is you can calculate an approximate gradient with only two function valuations, no matter how large the true D is. So if you have a billion parameters which you're trying to optimize, you still need only two function valuations. But the bad news is that as time goes on, the variance blows up. Okay, so what do you do then? The next theorem will talk about that. So all these adjustable constants that satisfy these assumptions, I'm not going to spend much time on these slides, except one thing I want you to focus, and that is right there, which is that my momentum parameter has to be bounded away from 1. Okay? But summation of alpha t bt is finite. How can that happen? Only if bt goes to 0, right? So let us assume that not only bt goes to 0, but it goes to 0 at a known fixed rate, t to the power of minus gamma, right? And similarly, m of t is allowed to blow up, but I assume that it blows up no faster than some rate that I know. So what happens if bt is identically 0? Then I take gamma equals 1. And if m is bounded almost surely, then I take delta equal to 0. So here is the statement. You choose a stepsize sequence which looks like t to the power of -1 minus phi Okay. And it cannot go to 0 too fast. It's bounded both above and below. And how do you choose these constants phi and c? Phi is smaller than the minimum of 0.5 minus delta and gamma. What are 0.5? So gamma is the decay rate of the bias, and delta is the growth rate of the variance, right? So you choose this exponent and the step size to be no larger than the smaller of these numbers. Okay. So if gamma is 0 and delta is 0, gamma is 1 and delta is 0, this just becomes a familiar condition of 0.5. Now here the point is, if you define an auxiliary constant nu to be this number, now it's an explicitly computable constant, because you know delta, you know gamma, and you are choosing phi. Then for any number lambda that is in this interval, the norm of the gradient squared converges at least as fast as t to the minus lambda. And the objective function itself converges at least as fast as t to the minus lambda. So j converges to 0 and the gradient converges to 0, but you have bounds on the rate of convergence. Okay? And in particular, just reminding you what these symbols mean, if I choose phi arbitrarily small, that means I choose the step size to be 1 over 1 minus t plus some really small number, then the rate of convergence is essentially 1 minus 2 delta or gamma, whichever is smaller. In particular, you go even more generally, if bt is identically 0, meaning no bias in the gradient, then I said that you choose gamma to be 1. And if the function, the variance mt is bounded, then choose delta equal to 0. So then what does this number become? Just becomes lambda less than 1. So the rate of convergence when you have unbiased gradients and bounded variance is arbitrarily close to 1. Okay. Now, there are some papers in the literature which show that for convex functions, lambda to the minus 1, t to the minus 1 is the fastest available growth. Okay. Now, I don't quite have that. I have t to the minus lambda arbitrarily close to 1, but I don't assume convexity. So that's the big jump. Okay. So what I'm showing is that if you have functions of class PL, the rate of convergence pretty much matches the best possible rate. Okay. You know, I have a little more time. I wish I had put in a few more problems for research. Anyway, so we just ran a few examples. This is a kind of a quadratic function plus constant times sine squared theta. This is a class of PL, as you can imagine. But because A is a block 1000 by 1000 Hilbert matrix, and there are 1000 of them, this matrix is really badly conditioned. And but we chose this constant C so that J belongs to class PL. And we simulated not only gradient descent when heavy ball and nag, but also ADAM, ADAGRAD, and RMS prop. And with just additive noise in the gradient, all the algorithms more or less performed well. But when you use zeroth order approximations, now you have biased gradient and blowing up variant, Nestrov's algorithm diverged. So one of the things I've been trying to do is, what are the papers in the literature on the convergence of Nestrov's method with noisy gradients? Okay. So I've not found any theorem which says when the conditional variance blows up, the algorithm will converge, because it doesn't. Here are examples to show that. But the other interesting point is stochastic heavy ball, this really old algorithm, more than 60 years old, outperforms all these modern algorithms. Okay. Now, this is the slide where I wish I had if I timed this talk properly, I would have put in a few more materials. So let me see if I can just talk. So first thing is that our results are quite comprehensive with one exception. What is that exception? It's right there. I assume that the momentum parameter is bounded away from 1, which makes it not applicable to the conventional Nesterov method. So one of the things I'm very curious about is, can this sort of a martingale convergence approach be used to prove the convergence of the true Nesterov method, where mu t approaches 1 from below, right? I don't know. Now there's a very interesting paper by Shu, Boyd, and Candish, in which they don't have any noise. They assume everything is perfectly noise-free measurement, but they approximate. See, one of the things I should tell you, I mean, I have a couple of, I'm now 44 minutes. What time you want me to stop? 50? Then I have 10 minutes for question. Okay, I'll just take 2 minutes to talk about it. So they assume there's no noise in the measurements, and then they look at the so-called ODE approach. Now, because of the momentum term, the ODEs for all these momentum-based methods are going to be second-order equations. They are not first-order equations. Then they analyze that, and they come out with this very cute result, which I honestly don't understand, that this is the optimal schedule for the momentum. Okay. Obviously, it approaches 1 as t goes to infinity. But this is all assuming strong convexity. So if there's one thing I've learned in working on this problem over the past 4 or 5 years, it is that last beautiful results that hold with no noise in the measurement simply don't work when you have noisy measurement. Okay. So I try to figure out what can be done when there is noise. And my last topic is, I use something called the Robin-Sigmund theorem. Everybody uses that. That's the most powerful tool. So it turns out that in doing this proof, I have to apply this Robin-Sigmund theorem. And that's where I wish I had thought of putting the slide. Next time I know what I'll do. I'll put in the slide and skip it if I don't have time. I think it's a good lesson for me. So it assumes a certain basic inequality that holds from time 0. So in this problem, in my proof, it turns out that that inequality does not hold from time 0. It holds at some random time, which is path dependent. But what saves me is that even though this time is path dependent, there is a bound which is not path dependent. So that's a very interesting research problem. Is there a version of Robin-Sigmund theorem where the inequality holds starting from some random time onwards, and the random time is path dependent and is not bounded almost surely? So my good friend Professor Karandikar and I are trying to work on this. So another point is, are there other classes of invex functions that are readily usable besides PL and KL? And there are other methods like RM and RMS prop to which my analysis as it stands now doesn't apply. There are some proofs of convergence. I shouldn't say no. Maybe I should say very few. But mostly the utility of these algorithms is established only by simulation. So basically, there is a saying that if you have a hammer, to you everything looks like a nail. So maybe I'm guilty of that, in the sense that I have this very powerful theory, and it's not my theory, of course, but Robin-Sigmund. So I try to figure out what are all the problems I can solve using that. But it will be interesting to see if there are other problems to be solved. This is a bibliography of all the papers. You can share this. You can share this with the people if you want. I found about 3 typos. I'll fix them and mail it back. Okay, thank you.
Yeah, we have time for
So
like, can you give some insights into what is causing that gap? Like, you are almost there to 1, but not exactly. So, because for SGD you can show for PL functions exactly 1 over T rate. So, what is causing the gap in your analysis?
So it's just a summability condition. You want various sequences to be summable. So if I put gamma exactly equal to that, the summability condition blows up. That's all.
And one more comment. So, like you said that other than Nesterov, like going further back into the sequence, like so there is something called Chebyshev-Anderson acceleration. Like, is that what analyzes a window?
Yeah, but yes, I know that, but it's kind of fallen out of popularity, right? I mean, my point was, if you're going to go back one time step, why not arbitrarily many time steps? And does that offer any advantages? So my guess is the fact that nobody has studied them means that way back when people must have done simulation and they didn't find any advantages. But that's only a guess on my part because I haven't looked at the literature way back then.
Thank you.
I think Gohan has a, yeah.
So you mentioned about the stochastic heavy ball and other methods, and you proved some convergence rates. At the level of convergence rates itself, do you see any benefit of using this momentum? I'm asking this, maybe I'll just add one more thing, because at least in least squares and quadratic optimization, it has been observed that if you take your stochastic heavy ball and those kind of methods and use the vanilla stochastic gradient with a different step size, it seems to be matching the performance of heavy ball and so on.
Yeah.
So it's not clear if you are able to quantify the advantage of using these momentum techniques. Thank you.
I'm familiar with those papers. You cannot prove any universal advantages. This I can say. So if that's your point, then I agree totally. However, all those examples you are talking about, they assume a lot of very specific information about objective function. I would say the advantage of these theorems is you assume nothing about the objective function other than that it satisfies PL or KL. Now, if I say that I have a quadratic function, and that's all I know about it, then the fastest achievable rate is only t to the minus half. You know, if you can't keep playing with the algorithm to use specific knowledge about the cost function, then stochastic gradient descent doesn't go faster than t to the minus half. So that's the way in my mind I think about the advantages of heavy ball or Nesterov vis-a-vis gradient descent is not that it is always faster, but that it is always universal. Do you understand what I'm saying? What I'm saying is, okay, this converges, let me say t to the minus 1 for the sake of argument. So this converges like t to the minus 1. Are there situations where stochastic gradient descent will also converge at t to the minus 1? Yeah, sure, but not universally. Whereas this is a universal statement. No matter what function it is, this is a guaranteed rate of convergence. And that is the way I think about it. So just to repeat what I said, the way you get gradient descent to match heavy ball is by doing a lot of tinkering, assuming the specific knowledge about the objective function. That's how I think about it. Does that satisfy your question? Yeah. Okay, all right.
Thanks, first of all, for this wonderful talk. So, is it easy to go from F to F, which is stochastic, and the objective being expected values?
Yeah. If you're saying in the case where J is the expected value of something else with respect to some probability distribution. That's what you mean, right?
Yes.
So, for example, then what happens is, so you actually wind up calculating the objective function itself in a stochastic manner.
Right.
Like mini batch optimization, for example.
Correct.
So then all this theory goes straight through. No problems.
Okay, so
if you have, let's say, J is a big expected value of something,
right.
you calculating the true expected value is too messy, so you approximate it by just sampling according to that measure and use that as the objective function, and you keep changing from each iteration. Then all this theory goes through.
So do you need any extra assumptions that these sample gradients or these sample updates are in some sense aligned to descent?
No, no, no.
You wouldn't need any of that.
All you really need is that the difference between all you really need is that the true objective function is the expected value of some function with respect to some probability measure which you know. Now life gets really interesting. If you say my objective function is the expected value of something else with respect to a measure that I don't know, and that unknown measure manifests itself through these samples, then you have one more layer of complexity. So that is this whole business of Markovian stochastic approximation, where the probability measure with respect to which you're taking the expected value is the stationary distribution of some unknown Markov process. And the gap is quite a lot. That makes the problem quite a bit harder. But if you assume that you know the probability distribution and you have the ability to draw IID sample, the theory is not harder. Theory is not NOT harder.
Got it. Understood. And just quick one more question. So if we replace the Lipschitzness by a local Lipschitz property, then can there be some modifications?
No, I'll tell you why. See, let me look at this condition. All you have is a bound on the variance, which means the difference between h and the true gradient can be arbitrarily large. So the global Lipschitzness of the function gradient means that no matter how large the disturbance is, there is a priori bound on how far off you are kicked away by this error.
Got it.
The minute you make it local, then you may be kicked off so far that you cannot recover.
Correct.
Now, there is a very old paper by Leonard Jung, which as far as I know, nobody has followed up. Okay? And he almost makes it like a throwaway observation. He says, well, don't just assume this. I mean, his notation is different, but basically what he's saying is, don't just assume finite second moment of the error. Assume finite second, third, fourth, fifth moment. Eventually assume the noise is bounded so that it has bounded moments of finite moments of all orders. Then you can do something with local Lipschitz, because if you know you're here and the noise is bounded, there's an a priori bound on how far you can be disturbed. But if you're going to restrict to this kind of noise, and remember this assumption permits very weird noises, then local Lipschitz is usually not enough.
Got it. Because you mentioned the Robin-Siegmund, and the variance appears in sort of the last term in the right-hand side, I imagine.
Yeah, that's what I do. I mean, my generalizations are fairly true.
Right.
But yeah, that's what I do.
Right. So there, I mean, we also, Professor Bhatnagar and I, also working on similar things. And there we control it by clipping, because we don't assume Lipschitz. We are not doing heavy ball. And like you said, we are sort of seeing how far vanilla gradient can go. So would something like that be, in some sense, possible here? That is, remove the assumption on local Lipschitzness, but do something like clipping, but then you're adding some kind of bias to the estimate of the descent.
No, I mean, I'm not going to be bold and say it's not possible. I think there's a lot of scope for useful generalizations.
Okay.
It kind of goes back to what Guhan was asking, that can you prove any universal improvement?
Okay.
And I think the point is that in specific situations you can always get improvement. But you have to, in order to really make an impact, you should show some kind of a universal improvement.
Understood. Thank you.
So let's thank again Professor Vidyasagar for that very nice talk.
Research scientist at Google DeepMind. This research interest currently focuses on diffusion-based generative modeling for text and multimodal data. He completed his PhD at Lab for Information and Decision Systems at MIT, advised by Professor Guy Bressler. And today, Dheeraj will be talking on fine-tuning diffusion models via intermediate distribution shaping. Thank you.
Can hear me? Okay. Okay. So yeah, thanks for the kind introduction. I'll be talking about RL algorithms in the context of generative AI today, and this is based on some of my recent work, which is still under submission. Okay, this was done with some of my wonderful authors, Gautam and Nitish, who are predoctoral researchers, and Karthikeyan, who was a research scientist, Shan was my intern, and Sanjay was a professor at UT Austin. Okay, so let me delve into this. I want to first clarify that I'm not an RL researcher per se. I have dabbled in RL problems because I work on optimization and generative AI. So we can figure out some of the details together if I get some stuff wrong. So, yeah. So, okay, so let's look at generative modeling and RL alignment. So what do we do with pre-training generative models? So the problem is as follows. So you have x1 to xn, which is drawn from some distribution P, ground truth distribution. And then the task is to obtain more samples approximately from P, right? So this is basically what the pre-training objective is. For example, we might have crawled the entire internet for data for LLMs, and then what we want to do is generate 1024 words, right? Each sentence, and then these chunks of those is each sample, and we want to produce those samples from the same distribution by just looking at internet data, but they should not be like exactly the same. It should be new sentences. Okay, so similarly, the diffusion models are the ones which are mostly used for generating images, right? So, and here the kind of data sets are like Lion 5B, which has 5 billion images with captions, which has been crawled from the internet, right? So, okay, so first thing is if we go and just take up so much abundant data from the internet, it might not be pleasing to the human eye. It could contain complete garbage. Like if you just go and sample a random sentence from the internet, it's probably garbage, right? But it has some semantic information in the sense that it can tell you how to write a kind of grammatically correct sentence, how words are put together and what words belong together and what don't, and so on. So there is some information, but there's a lot of garbage which we don't want it to learn. Okay, so that's why we go into post-training and RL alignment, right? So pre-training is just mimic the data given the large corpus of data, and post-training is make it more structured and more palatable and more digestible to the people who actually read it. Okay, so here one thing people do is instruction tuning, that is given a question X, we want to generate a correct answer Y given X, right? So initially what was the data? It was just there'd be some paragraphs upon paragraphs of things. Maybe there was a book, right? And you just want to write, given so much, you want to produce the next. But here specifically how we wanted to interact with us is that we have a question X, questions have some kind of a distribution, and we want to sample Y given X, that is the answer to the question. So we wanted to follow our instruction, and maybe there is another question based on that, and we wanted to look at what it has answered, what is my next question, and then answer, right? So that is a distribution shift compared to what we crawled from the internet. Okay, we might want it to refuse to answer harmful questions. So maybe the classic example is that, okay, you might go and ask them to how to make some kind of an explosive device, right? And you need it to actually go and say, recognize that this is harmful and say, no, I'm not going to do this, okay? Okay, so we want to increase the factuality of answers. Like I said, pre-training data has all sorts of sources and all sorts of, I would guess that there are a lot of conspiracy theory forums which get crawled into this. And then it will have a lot of nonsensical information. And we don't want that repeated here. We want factual answers in this thing. Okay, and when it comes to generating images, we want to make it pleasing to the human eye. So if you go and take a random picture crawled from the internet in some forum, it probably does not look good. It's a picture which has people, it maybe respects laws of physics in some sense, humans have the correct shape and so on, but when you wanted to generate something, you might want to have the right contrast, right brightness, right photographic quality, and you want it to follow what exactly you want it to. Like if you want them to be want long hair, for example, it must actually adhere to that, what we want to see in that. Right? So we want to also make it pleasing to the human eye. Right? So these challenges are tackled typically in what we call post-training. Right? Okay, so for example, we also might want to improve the aesthetic quality and readability of the generated text. Okay. So how is this usually done with RL alignment? It's that, okay, you're given a question Q and an answer A, and we obtain a reward model R Y given X for each task. Okay, so there is no single task here. Each of them has to be taken as a different task. For example, increase the factuality of the answers is a different task. Okay, right. Refusing to answer harmful question is a different task with a different reward, and increasing aesthetic quality of and readability of the generated text is a different task. For example, here you reward how nice it is to read rather than factuality. So you have a multitude of tasks and multitude of reward functions, and you want to maximize this for this given question and answer, given that your model answers this, right? Okay, so this is roughly this setup we are going to deal with. Okay, the task is to tune the pre-trained model, which is trained to mimic a lot of low quality data and generate answers with high reward value for all these different kinds of rewards. Okay, so let me tell you a bit more on how this R Y given X is taken. So you actually go to humans and you show them two generated text and you ask them, what do you prefer? And you might go to experts and say, okay, what do you think this answer is? And then they'll give you some answer. And then you train another model which tells you how rewarding this is. For example, if you, for aesthetic quality and readability, you show two answers generated by the same LLM to the person, and the person ranks them. And based on that rank, you fit a model to get a reward based on something like a Bradley-Terry model, right? So this is a learnt reward function, which we take to be ground truth, but things like reward hacking is very much possible because of this setup. Yeah.
Can these rewards be adversarial or wrong rewards?
There are some wrong things there because you don't have infinite data because it's inherently learnt, right? So if you start going very out of distribution, you might it might start rewarding long answers, for example. Right, because people might associate long answer with correctness. So it's not correct, but just because you see long answer, it might start giving you higher reward. So it will start on rambling on and so on. That has been seen. So a lot of things happen that way, especially when you move away from the distribution on which the reward model was trained for. Right. So that's still under research as to how to mitigate these biases. Okay. Okay, so this was my task. Okay, so let's look at more mathematical setup. You have P naught of y given x. This is the likelihood of answer y given question x with respect to reference model, that is the pre-trained model. Okay, and then we have P theta of y given x, which is the likelihood of answer y given x with respect to policy model. Policy model is what we are trying to tune, and we'll keep a copy of the reference model here just so that we don't move away too much. So what is solved in this context is something called the entropy regularized reward maximization. Okay, the first thing we want to do is we want to maximize a reward of y given x, expectation where y is drawn from p theta given x. Okay, and then we add this KL divergence regularization, the relative entropy. So we do not want this to move too far away from the pre-trained model. Okay, so why do we not want this? Like I said, this reward model itself is trained on a certain distribution, right? If you start moving far away from this distribution, it starts giving you nonsensical results. Like I said, if your answers start getting too long, this will start rewarding long answers instead of factuality, for example, right? So, and also you have multitude of rewards, right? It's not just aesthetic quality or harmful questions or factuality, it's just tens of rewards you might want to train on. So if you overtrain on one reward, something like mode collapse happens. So you completely forget all the data and knowledge you learned in pre-training, and you just optimize this, hyper-optimize this one thing, right? So because of this hyper-optimization, it becomes useless for every other task, and there will be mode collapse, right? So what we want is that we want to maximize this reward, but we also do not want to move too far away from what I had pre-trained on this large amount of data. So we are looking for small deviations from the original model, which improves reward. And this is a standard form which was actually proposed by Stienon et al. In the case of reinforcement learning with human feedback. But it has been extended so much that it doesn't have to be human feedback. It could be verifiable rewards, for example. It's you give it a math problem and it will do give some answer, and then you just say, is the answer right or wrong? It's a verifiable reward. You don't even need human feedback, right? So all sorts of rewards are possible now. Okay. So like I said, this wants to maximize reward, and this wants you to stay close to the prior trained model. Okay, so let's look at how this is classically done in autoregressive models, right? So in the case of autoregressive models, you have a neural network, and initially there is no input to it, or let's say X is an input to it. It will first generate first letter, let's say G, and then you feed this token N, and then it generates E, and then you feed as input G and E, and then it generates N, it gives you GEN, right, and then so on. It generates things one by one, autoregressively. So mathematically, how do I look at it? It's like you have a answer y1 to yn, so there are n tokens, right? Let's think of them as these 8 things, G, E, N, E, R, A, T are different y1 to yn. So how we know a factorization of this, given a y, I have this following factorization. What is the likelihood I generate y1 given x? What is the likelihood I generate y2 given y1 comma x, and so on, till what is the probability I generate yn given everything before n and the question. So this is fundamentally known by the model, and we can fundamentally compute this in the sampling process. So we can compute this, and once you know this in the model, you can go and plug it into the KL divergence formula. And we can actually compute the KL divergence, or a stochastic approximation, unbiased stochastic approximation for the KL divergence, right? So there is no problem. We can just implement this with your favorite RL algorithm, right? So you can just put this in, you have an estimate for this entropy regularized reward or relative entropy regularized reward, and we can use the favorite RL, policy-based RL algorithm. I think PPO is the standard, but there are new things like GRPO, etc., which gets rid of the critic network. It only has an actor network. And we can use all of this. I think even reinforce actually works quite well in this thing. You don't even, many people don't even do variance reduction, and you get very good results here. Okay, so now the topic, let's come to the topic of today's talk, which is how do you do this with diffusion models, right? So let me tell you some challenges with trying to come up with the same question in the case of diffusion models, right? So diffusion models work fundamentally in a different way compared to autoregressive models. They generated token one by one. This works by denoising some complete white noise into something which is data, right, which we think of as a sample. Okay, so for example, here we think of, let's say our input is x is equal to, I want to generate bicycle. Okay, I start with y5 here, which is complete white noise. It has no relation to bicycle whatsoever. And I'll make it slightly less noisy, and then slightly less noisy. This is y3, this is y2, this is already looking a bit like a bicycle. Then this is y1, and this is y, which is my output. Okay, it's a low resolution CFAR image, but we can make it high resolution and make it look actually nice, and so on. So finally, your output is y0 is equal to y. So this is how our diffusion models work. And in this case, we only have access to conditional likelihoods, right? Okay, so I'm given yn and this x, that is slightly noised version, and x, and I want a slightly less noised version, yn minus 1. I know these conditional likelihoods from my model, right? And I don't know anything else. So from this, I cannot compute the marginal likelihood p theta of y given x. Right, so reward model doesn't care what the noise is and so on, how you generate it. You just see the final answer and then say, is it good or not? What is, how good it is, and so on. but now you cannot get this KL divergence with respect to this likelihood. So you cannot do KL regularization, and this is a fundamental problem in doing RL alignment with diffusion models, right? Okay, so so given this the case, so a lot of people have looked at it for the last 3-4 years. One is to use relaxation, various kinds of relaxation. Why do we need marginal KL divergence, right? So people use trajectory KL divergence instead of marginal KL divergence, right? So what do? You look at the joint distribution of the entire trajectory, y0, y1, y2 till y5 under your current policy model versus y0 to y5 under your base model. This can be obtained using Bayes rule and the chain rule for KL divergence. This can be calculated. And once you do that, you can use this regularizer instead of your marginal KL regularizer. This is called DPOK, and this has been around since 2023, for example. Okay, so what is the problem here? This can lead to subpar results, right? Because you have this whole trajectory and you're not letting it deviate from the original trajectory at all. You want to maybe move a bit more, but you're constrained in the entire trajectory, and this can be too conservative and to allow you to do anything here, right? And we know that this can lead to subpar results. This was shown in subsequent work that it might not be the best thing to do. And this also has something called the initial value function bias problem, because when you're imposing this constraint, you have to use the learned trajectory, and there is no mixing in some sense. You have learned it imperfectly. And because of lack of mixing, it changes the reward function in ways hard to predict. You don't actually get the equivalent solution. The final solution you get here will change the reward function in some sense, because here in ideal case, when the things are perfectly learned, where you start, that is a pure Gaussian, will not be able to predict what reward you end up with. But if you use an imperfectly trained model, which is almost always the case in practice, you can usually predict something about the final reward given the initial noise you start out with. And that causes a problem. That causes a tilt because of imposing this kind of a KL trajectory-wise regularization, right? And that can have some kind of a spurious effects in your further modeling. Okay. So how do we fix this? There are more ideas here. The other one, which might be more closer home in this workshop, is DDPO, which is that, okay, we just remove KL regularization, we don't care. So for example, if you want to design a molecule or something with diffusion models, you want to care about the correct structure. You don't care about diversity or anything. Why should it be close to this? Image also, it's like we have a hyper-specific prompt. I want this tall person with this shirt, this pant, with this kind of a haircut standing in front of this background. It's already hyper-specified, so it has to generate that. That's all. I don't care about the diversity or any other thing. If I want to do that, I'll just remove the KL regularization. Okay, so now we have a natural MDP coming out of this. Okay, what is my Markov decision process? Which is we have yn, which goes to yn minus 1, we goes to y0. So we take a Markov a kernel, apply a Markov kernel, and the decision in this case is the parameters of the neural network, which parameterizes the posterior distribution given yn, distribution of yn minus 1 given yn. And we apply this and we end up with this y0, and we have a reward for y0, right? So the action here is the denoising kernel parameterized by a neural network, and then you just maximize the reward with your favorite RL algorithm, let's say PPO. You're given rewards, you're given action space, and apply PPO. Yeah. Yeah, so basically it's a neural network, okay, which will, okay, this is a stochastic differential equation, right? So you have to specify a drift at each time. A drift. Okay, so the drift is specified at time t given at x by a neural network, and usually you discretize it, so you can assume that it is just a mean and a covariance kernel. So it specifies the posterior mean in some sense, and once you do that, you can do that, and once you tweak it, that's how you get the RL tuning here. Yeah. Okay, so let's say the action is this. Okay, you want to obtain yn minus 1 from yn. Okay, so usually how it is, you have yn minus 1 is equal to yn plus some mean plus some Gaussian random variable. Gaussian random variable has some variance. Variance is fixed. So you add some mean to this, right? The drift. The drift is a function of yn. Or the drift is the action. So it's a continuous action space kind of thing. So it's kind of like stochastic control. Basically, I think this is solution to some kind of a stochastic control problem. There is a thing, but I don't know enough to comment more on that. But basically, the action at each step is how much, what is the mean of the Gaussian you add. You add a Gaussian at every step, but what is the drift you add to that, depending on the thing. That's what you add. Okay. Reward is something we get from real life. Someone gives me the reward. Right. For example, let's say one reward example is that I give X as bicycle. Does the final image I generate contain a bicycle? So if it is, it gives a reward 1. But if it's like a partially occluded bicycle, it gives you a 0.5. You don't get the reward till the very end. That's the thing. So it's like a destination thing. So that is part of the problem in here. So you only get a reward at the end. So but what we are doing is we are not training it purely through RL. We are not pre-training through RL. So what we train is already almost good enough. So about 50% of the time or 80% of the time, it already generates a nice bicycle. Right. So what we want to do is we use our algorithms to make sure that it generates 100% of the time or 99% of the time. So I think that you need more dense reward to train it from scratch. But because you have sparse reward, if you have something which is already good enough, you want to make it very good. That's the goal we have. Yeah. So this, the mean itself, the action itself, let's think of it as you append it to the state. It's an unchanging state, let's say. Let's think of it that way. Right. So you can actually fit an MDP in this case, in some sense, right? And then you get a reward, and then you use your thing, and it works. So the problem with this is that, as was expected in the LLM literature, then the fundamental reason the KL term was imposed was because it causes mode collapse, and once you actually go to large scale training, right, you just won't have one bicycle and you want to get this, you will have thousands or hundreds of thousands of things you are actually optimizing for, right? And there are very many diverse number of prompts, and it becomes unstable at this point, and it might even forget where it started out with. It might actually cause worse performance than you started out with, for example, if you remove it, because you go too far and you can't trust your reward function anymore. Yeah. So you can get a sparse reward MDPs, right? So for example, if your MDP is that you reach a goal and you get a reward. So it's a sparse reward MDP, but your actions and states matter what you did before. Okay. Just that you only goal state gives you a reward, non-zero reward. Everywhere you get a 0 reward.
Okay, sure.
Right, so okay. So what we did in this work is we went back and said, okay, we are thinking too much in terms of RL algorithms. Can we take a step back and see if there is any backdoor way than imposing and explicitly computing the scale divergence and so on. So we look at it from the lens of rejection sampling. We go and say, okay, there is this very specific structure we have. It's not some arbitrary reward. We have this scale structure. And can I just solve this? What is this P theta star? If I say theta star is the thing which maximizes this parameterized probability distribution, then we know that by method of Lagrangian multipliers, it is a tilted distribution. It is tilted by this reward R y given x divided by beta, right? So what does it do? It just upweights, it increases the probability of getting higher reward samples by an exponential amount. And this beta controls how much I tilt it, right? So this ensures that I don't actually forget where I started out with. It's just that I make the better answers more likely, like I said. So, right. So here, let's look at what rejection sampling does. How do you, okay, let's say I don't want to find theta star. I just want to sample from P theta star. Okay, there is some, in statistics, this is called rejection sampling, right? So you have y you take from the original model P naught given x, and you accept or reject y. So you accept y given with the probability e to the r y given x minus r max divided by beta, where r max, let's say, is the maximum reward value. Usually it is 1, right? And then you do rejection sampling. If otherwise it's rejected, right? And then you look at the y given x comma accept. conditioned on the question being x and y being accepted, what is the law of this? Then we can show that this is actually distributed as this tilted distribution, right? P theta star given x. So this is the classical rejection sampling which is used in statistics all the time. Okay, so this actually gives us an alternative to RL algorithm. So what do? We create a large data set of accepted samples. Now we know what is the distribution I want to generate from, and then I go and fine tune on these accepted samples using the pre-training algorithm. I don't have to use RL. I just collected a new data set. It is of a higher quality because I filtered for the low values, and then I'll use my pre-training algorithm because I know I have a higher quality here, right? So this is called fine tuning, right? If you come up with some high quality data points and then you tune it on top. So this should improve the thing. Okay, so the advantage here is that you don't actually need to do marginal likelihood computation. I don't care how I generated this, what model generated this, is it diffusion, is it autoregressive, doesn't matter, right? So the advantage here is that we don't need marginal computation. That the drawback is that the acceptance rate can be very low. So you are doing a lot of generations before you are even able to accept one sample, right? So initially, suppose you start out with a very low reward, the R minus R max could be so small that you accept only 1 in 100 or 1 in 1000 samples. So you are making your algorithm very inefficient. Yeah. Yeah. Step 2, yeah. So you can keep on bootstrapping on top. So what do you do? Okay, so the principled way of doing this is this. Okay, I'll generate a lot of samples from this data set, right? And then I'll just forget about the thing. I'll start from P0, and then I'll train the algorithm to generate from this new data set.
So it is iterative algorithm. It is iterative, right?
Iterated, yeah. Iterate the pre-training algorithm, right? Okay, but you can keep repeating it again and again too, for example. Yeah, whatever your pre-training algorithm was, so initially you had a lot of garbage data and low quality data. Now you replace it with your new nice data you generated yourself, you filtered it, and you apply fine tuning on top. No, it implicitly gives scaled. Okay, so why do you, this form for P theta star, right, comes up because of scale regularization. Right, so no, it's already close to P0 because I generated from, okay, if you go back, I generated Y from P0 and then accepted or rejected. So it cannot be far away from P0 because if I generate say 1000 and accept 100, it is still probable that it was generated by P0. I have not moved too far away from P0. Right? So, yeah. Yeah, it can apply to any generative model. Direct preference optimization actually uses this to actually get reward and fit a reward to Bradley-Terry model, and it's a different backdoor to doing yeah. Right. So in Bradley-Terry model, what happens is that you have preference data. And so in PPO, usually RLHF, you have preference data and you fit a Bradley-Terry model on top. So DPO folks asked, I don't want to fit anything on top. I just take the preference model and then directly do it. And then for that they use it. But here we don't care about that. We are just given this reward function, which tells you some aesthetic quality or something. Right? So, yeah. All right. So, okay, so the advantage here is that you don't need marginal likelihood, and disadvantage is that it can have very low acceptance rate and which can hinder efficiency. Yeah, so there are many efficient proposals here, right? For example, one of them could be I'll generate y1 to yn from P0. I'll calculate the reward r of yi given x. It's not ri, it's just r of yi given x. And I'll accept the top k out of n here, right? So I've assured that I have ensured that I can at least keep k out of n samples here. It's not like arbitrarily small ratios. Let's say n is 10 and k is 4. I keep at least 40% of the samples every time I generate through this kind of rejection sampling, right? So it's not too bad now. It's actually efficient. Okay, so some bibliographic notes. So RAFT was originally proposed by Dong et al. In 2023, right? And this is called rejection sampling fine tuning. And then rejection sampling based ideas have been used in a lot of RL based fine tuning here. It's also called best of n alignment in LLM literature. That is, you generate n answers from itself and you keep the best answer and you fine tune on that, right? So you want to align it to the best version of itself in some sense. Okay, so how does this work? Okay, you have an input X, you have a pre-trained model. This is called generalized rejection sampling fine tuning. And then we generate multiple samples, in this case 4 independent samples given the same input, right? So and then we accept high reward output. So we have multiple outputs from this. Let's say y1 and y3 have high rewards. How I obtain it is whatever I decide, right? I don't care. Right now I'm abstracting that out. It doesn't have to be a specific way of rejection sampling. And then I'll collect a data set out of this and retrain with these accepted samples, right? So this is called GRAFT, that is generalized rejection sampling fine tuning. Okay, so in the most general format, what I do is that I have samples y1 to yn and rewards r1 to rn, and I'll sample I with probability pi is equal to acceptance of ri f hat r, yi and p hat y. What are these? Ri is the reward of sample I, and f hat is the empirical CDF of the reward functions. Okay, so for example, it allows me to pick the top k thing in the top k out of n, for example. Yi is my current sample and p hat y is the empirical distribution of y1 to yn. So this can help us with, for example, deduplication. If I am answering the same, giving the same answer all the time, I might want to deduplicate it. So I might want to reject it, for example, and it can capture that. So given a sample I accept it with probability pi, which is some arbitrary function of these variables. Okay, then we can show that the law of yi conditioned on acceptance with this and x, the question, solves the following entropically regularized reward maximization problem with some new reward r hat. I had an original reward r, but then if I just do rejection sampling and accept samples in this way, the accepted samples, the law of the accepted samples are a solution to this reward maximization problem, where r hat is this log expectation of this acceptance probability, right? So this is actually a monotonic reshaping of my original reward. So when I'm solving this problem, I don't care if I maximize r or some monotonic reshaping of r, which is r hat. So I'll just say I might as well go ahead and do some nice rejection sampling which is efficient and maximize r hat instead of r, right? This solves scale regularized reward maximization with a reshaped reward. Yeah. Fr hat is the conditional distribution function empirical CDF of the rewards. So for example, it tells you what percentile of the rewards it is in within R1 to Rn, right? So suppose you want to get top 10 percentile of the samples, you can do that with that filtering. Okay, so let's look at an important example. We have something called a preference reward. So I'll generate y1 and y2, and I'll accept y1 if r1 is greater than r2. Otherwise, I'll accept y2. Okay, so then r hat of y given x divided by alpha is this empirical CDF of r of y given x. So I've reshaped it. So we know that the sorry, not empirical, it's the CDF, population CDF, and we know that CDF is a cumulative density distribution function, is an increasing function of its argument, right? So we have monotonically reshaped this reward to get the new reward, right? So I solve it like this. Okay, so basically reshapes to this and it's monotonically increasing. So in some sense, if I maximize r or r hat, it shouldn't matter, and this is a backdoor to do this. Yeah.
So why have you chosen only this monotone function?
No, I can choose anything. So I gave an example.
Okay.
Right. So we have all sorts of things. So top k out of n or top k out of n with deduplication, right? There all sorts of things are possible. Or you can actually sample it proportional to the reward. That's called reward weighted regression and so on. So all those things fall into this category. Yeah. Is there any other question? Okay. So I showed you that this graph actually applies to any generative modeling algorithm. So can we do better given the structure of diffusion models, right? So we have a specific structure where you have a specific notion of denoising from a Gaussian, right? Yeah.
Sorry, one more question. So can you view this as some risk sensitive or risk seeking RL or something like that? Because instead of looking at the expectation of the reward, you are somehow looking at an expectation of the function of the reward, right?
Correct. Correct. So yes, you want to look at the distribution of that as well, right? So you want it not to be not far from there. You have the state, which is y, and the distribution of the state should not be too far away from some other distribution. If you actually write down the, in autoregressive model, this becomes clearer. Actually, you even per step, you have this minus negative log likelihood as a reward, addition to the reward. It's a tilted, in some modified reward, you add this term, penalty term to it. Yes, it actually rewards, should kind of link to the reward distributional RL in some sense. You were trying to maximize the quantile or something, but I don't know how exactly it connects in that sense. Yeah. In that sense, the risk is moving away too far away from where you started. Okay. So let's look at how we might want to get this. Okay. So let's say in this context, a reward is text to image alignment. So we want to use the structure of diffusion models. So let's say X is bicycle, and then I have this model slowly denoising starting from Gaussian to get a bicycle. Okay. So let's actually look at the structure. Let's say we go to the fourth step, and we say that it's already clear that it will generate a bicycle. Right? Should I even train the last step? I can just train the first 4 denoising steps. Why should I spend samples training this last step again? Right? So in some sense, okay, it might, there are some might be some bad cases, but most of the times I will generate a bicycle if I start here. Right? So okay. So with this notion, we came up with this called partial graph. We only train the first few denoising steps. Okay, you have an input X, and you generate multiple trajectories and multiple samples just like before using the diffusion model. And here a diffusion model goes through multiple denoising steps. There's a step n minus 1, step k minus 1, and so on until step 0 where it is the output. Okay, and we accept high reward outputs. There are 4 outputs here, 4 different samples we draw, and then we accept high reward outputs, and then we accept the y1 and y3 here, and then we only train for steps n to k. Denoising steps n to k. We don't train the last few steps, right? Because it just seems like, okay, my reward is already determined by now. Why should I consume extra number of samples to do this, right? So this is what we call partial graph. This uses the fact that we are doing a denoising diffusion here and not an autoregressive generation. Yeah.
How do you choose k?
Huh? That is empirical. Okay. I'll give you some things about how we might choose k, but that is, but there is some empirical flavor to it. Okay. Okay. So why would we expect this to work? Okay. So there is a bias variance trade-off here. Okay. So let me show you. You should choose it such that the bias variance trade-off is kind of best, right? So okay. So if I give you this image, reward variance is 0 because reward is a function of the final generation. Okay. So but if I give you this, okay, if I give you this image, okay, reward has some variance given this, because I only know y3, right? So given y3, what is the reward I will get finally? It has some variance. I can't tell you for sure, but I can tell you maybe it is around 0.4 to 0.6, but I can't tell you it is 0.55, right? Okay, but there is another trade-off called bias here, in the sense that the first few steps here are easy to learn, but the last few steps are hard to learn. Okay, and we give some theoretical evidence for this via Bakri-Emery theory. I won't actually go into the Bakri-Emery theory details of this, given in the interest of time. But this is, but we can show that there is some notion in which the learning gets harder. Okay, so so tell you to give you some idea about how this bias variance trade-off might look. Let me show you the task called molecule generation, right? So we have a large corpus of molecule structures, and finally we end up with a molecule, and then we want to, with the reward function is the molecule, resulting molecule should be stable. Okay, if it is stable, I give a reward 1. If it is unstable, I give it a reward 0. Okay, so let's say we look at the partially denoised thing, that is Tn, and then look at the variance of the reward x naught, given I have a partially denoised thing. Okay, at time n, it has a lot of variance, right? Because I have no idea where it will end up. But at time n over 4, this suddenly drops, in the sense that I can actually say whether I'll reach a stable molecule or an unstable molecule with some confidence, right? Okay, if you look at the distribution of the reward I get given conditioned on my current state, right? At binomial distribution is at time 0, right? Because you have no idea what reward you'll end up in, right? But if I condition on the partially denoised thing at time n over 4, this is not so binomial. There is some information about where I'll end up in. And if I look condition on time n over 2, this is deviating from binomial distribution more. And if I condition at n over 4, this looks very different from where I started out with. This is because there is a lot of information about what my reward will be given that I am here, given my denoised state, right? So just like if I show you this picture, you have some confidence that it will be a bicycle. It's the same thing with a molecule. Okay, so these are our empirical results which we used with stable diffusion V2. This is text to image fine tuning. So what is the reward function here? It is called the VQA score, visual question answering score, right? So you have a query from this data set, and then you want to generate a picture which adheres to this query, right? And how good they align with each other is the reward, and it is given by something called a VQA score model. Okay, that is my reward. Okay, there's something called GenAI bench which has a lot of these prompts. We took that and then we evaluated it on GenEval and TTY eval, and we also took other subsets of prompts to do this. We did rejection sampling based fine tuning and so on. So stable diffusion is a open source open weights model which can generate text to image, right? If you give it text, it will generate an image. So the reward we get is like 66.87, right, on its own data set, and then on validation data sets too, you get these kind of rewards. SDXL base is a much larger model. It has 69% reward. If I try DDPO, where I just removed KL regularization, the thing becomes worse than before because of instability. It is, if you remove KL, it kind of starts forgetting where it started out with, and its reward actually decays. Graft, which is rejection sampling fine tuning with top k out of n, that achieves a 70.7 reward, which increases from 0.66, right? But the best superstar of all is P graft, right? This partial graft where you only train the denoiser till the first 75% of the steps and keep the old model in the first 25% of the step. That achieves almost 72% on GenAI, and it beats every model, every other algorithm in training and validation with high confidence, right? So there is a trade-off, bias variance trade-off, and that doesn't show up at 0.75 n, it doesn't show up at 0.5 n, it actually starts showing up at 0.25 n, and we know this from the plot, okay? There is a similar task called layout generation. Here too, we see that around 0.25 n, we are able to get the maximal, and molecule generation, this difference is very stark because we had no idea, we had no algorithm which actually improves molecule stability over the pre-trained model. Baseline model had a 90.5% molecule stability, and then if I apply graft, it is marginal, it is within overlapping confidence bounds, right? And if I apply P graft 0.5 n, it is worse, but 0.25 n actually improves it, and this is the only algorithm we could use to improve this kind of a reward signal, right? So this has very good results here, okay? So I can actually take any questions on this because I can switch gears and in the rest of my time and go into something called inverse noise correction, which is not completely related to what is happening here. Yeah.
Maybe two quickly. So one, can you comment on instability? I'll also ask the second question. The other one on KL approximation. It's like, what approximation did you use? Did you use, I don't know, a Gaussian approximation? Can you please comment on these two things?
Right, so the whole point of this graft is that I don't have to use KL approximation here. Right, so you just use a pre-training algorithm, and usually supervised fine tuning is very, very stable. Especially with LoRa, and if you do it a few times, it's just very stable. We just did this graph step once, and then we just gave the results. There was no instability. DDP on the other hand is you need to tune the hyperparameters correctly.
Loss growing, or what is stability?
Yeah, so like catastrophic forgetting, for example, right? Suddenly you have some reward which is, let's say, 0.66, right? And suddenly the model stops being an image generation model, starts generating nonsense. Reward goes to almost 0, and it forgets its old initial. It's not doesn't behave like an image generation model anymore.
Got it. So you measure it using the rewards.
Rewards, for example.
Sounds
right?
good.
Yeah.
Thanks.
Yeah. Yeah. We tried 0.75, 0.5, and 0.25. I would guess this is a good enough thing. I don't.
I mean, is there any rationality that we can decrease it further and can have better result on that?
We didn't try it out at that granularity. We tried it only on 4 points, but yeah, it.
But yeah, that's remains a question, right? I mean, how it behaves when you decrease it further.
Yeah, I don't know that. Yeah, my guess is that given that at graph itself, which is at 0, again decreases. Maybe this is as good as it gets. But yeah, we should try it out. Yeah.
Because it's keep decreasing.
So, but okay, the noise level you see here is not like linear noise level. Yeah. It is already very, very close to the image once you pass this point. Okay. Right. So, in the sense that the scheduling is quadratic, in the sense that last few steps are actually the step size is very, very low in the denoising thing. It doesn't move away much from this. Okay. Right. So, yeah. Okay. Sure. I think I have 15 more minutes left. Is that right? 13 minutes. Okay. Okay. So let me switch gears and describe something which comes out of this. Some of these ideas. It's called inverse noise correction, and this is for improving rectified flows. You can see that the art here is very different from what I used before. It's because my intern made the slides in PPT, and I just stole it from him. And so okay. So how do flow models work? In flow models, you have dxt by dt is equal to v theta of t comma xt. This is an ordinary differential equation, and v theta is a neural network. So you give time and current position into it, and then you get the velocity field out of it. And then once you solve this, you want to reshape it such that you suppose you start with a Gaussian at x0, and x1 you want to reach the desired distribution. Okay, and rectified flow is a way to train these things. Rectified flow is a sister kind of models to diffusion models. There is a, if you read the stochastic interpolants paper, you can actually see that they're not very different. They're almost the same models, right? And up to reparameterization going from ODE to SDE, right? So for flow models, if you write this ODE, there is no bias variance trade-off, since the output is a function of the initial noise. So technically, the reward variance does not even increase, right? So if I just showed you some noise, you will be able to tell me what is the, at least statistically, able to tell me what is the reward on the final image, because you can just decode it with this deterministically and tell me what is the reward. So there is no trade-off here of bias variance at all. Okay, so this is a feature, not a bug. So for example, you might have some Gaussian noise here, and it will maps to this cat image deterministically. And if I give you a different noise vector or noisy image, it will point to this cat, and something else points to this, but it's a deterministic map determined by your neural network. Okay, right. So what you have is initial noise distribution, and you go through this discretized ODE, and you end up with the image distribution. Okay, there are several sources of error here. Okay, what are the two sources of error? One is the learning error, right? You had to do some statistical procedures to get here. So that will in itself have something like a statistical error. You don't have infinite amount of data, so you will end up with some error. And the second is approximation error. Your neural network is not infinitely large, so you'll have some approximation error. And the third is optimization error. Your optimization algorithm is not perfect, so you haven't reached the optimal. It's a non-convex optimization. Maybe you've not even if it was convex, you haven't reached the optimum, and so on. So there is these three sources of errors. We will call it a learning error. And the second one is discretization error. It's a continuous entity, this ODE, right? But you will solve it with something like Euler-Maruyama or something usually, and then that also accumulates errors. And if you use too few steps, you can't approximate curved paths well, and you get all these artifacts and low quality images. Okay, so the question we ask is, can we use some of the ideas we used before to correct these errors in a sample efficient way? Okay, so right. So only aspect we use here is that flow models are reversible, right? If you have a node E from x0 to x1 which follows dxt by dt is v of xt comma t, then if I write this new ODE which starts from x1 where I reverse the time and reverse the direction of the velocity field, I'll start from x1 and go to x0, right? So if you take capital T to be the Koopman operator, then the Koopman operator under certain assumptions on V is invertible. For example, under Lipschitz assumption it is invertible, right? So we have this invertibility. Can we use invertibility to do something here? Okay, it's reversible even with discretization because you have a forward Euler going forward, and if you do discretize this with reverse Euler, you actually get back the original point exactly. It is invertible even with discretization. Okay, so this is like Banach. This actually follows from Banach fixed point theorem that if it is Lipschitz, then even the Euler discretization is reversible, and we can do it with some effort. Okay. Okay, so here is how we will leverage this. We have a noise distribution, and this is a learned distribution. I will take x dot is equal to v theta of xt, but I will discretize this. This is my neural network which I learned, which goes here, which has errors. Okay, and then I can exactly reverse this with this, my minus v theta of this. Okay. So what we'll do is we'll take image distribution, but I'll apply my learned ODE with discretization back to something called the inverse noise distribution, right? So my noise distribution goes to learned distribution and back, but learned distribution is not same as image distribution. I'll take my original data set, but I'll reverse this. I'll get something called inverse noise distribution, which is distinct from the noise distribution. Okay, and if I reverse this again, if I apply my original neural network to this, I'll get the image distribution, right, which is exact. Okay, so now what I'll do is I'll have this noise distribution and I'll learn a model to the inverse noise distribution, right? So I've accumulated all the errors. What I'm saying is that if there's a learned distribution and a discrepancy between this and the image distribution, all of that can be captured between the discrepancy between the noise distribution and the inverse noise distribution, right? So all I have to do to fix these errors to one order is that I'll learn a bridge between noise distribution to inverse noise distribution. I'll train another model, right? So that will correct all the errors. And this should be easier to learn because we are mapping a distribution which is Gaussian to something which is approximately Gaussian. So we are not actually moving too far. The learning should not be too hard. We have some ideas using, we show some bounds using Bakri-Emery theory as to why this might be an easier problem, but it is still a sketch of why we, some theoretical evidence why this might be easier rather than a rigorous proof. Yeah.
So why should the inverse noise distribution have Gaussian structure?
So why? Because of data processing inequality or approximately Gaussian structure. So what I'm saying is learned distribution is not too far away from the image distribution, right? So now I'll apply data processing. I'll apply this inverse map here, T inverse here, and I'll apply T inverse here. So KL between these two should also not be larger than KL between these two. So in case these two are close, then these two are also close. That's the reasoning between that. Okay, so if I do noise to flow model and image with bad discretization, I get some images like this. But if I do noise and correction and then flow model, it kind of corrects the artifacts. For example, this image is messed up. This is slightly better. There is some artifact here that is better, and so on. Right. So this is inverse noise correction. We can actually show this. Numerically, you have something called Celebi data set. We trained a 65 million parameter model with a lot of steps, but then we had a small noise corrector, which is 16 million parameters, which is much smaller. And if you correct the inverse noise with this noise corrector, our quality, FID, quality is measured in FID. FID should be as low as possible. FID improves by a lot, as you see here. Even with 1000 steps of the pre-trained model, you cannot get something close to this. But just with 200 steps of this plus 200 steps of that, we can get much lower kind of FID, much higher quality images. This also can be replicated in Elson Church dataset. So this is a nice way to correct the errors here. Okay. This will be the end of my talk. I can take any questions you might have.
Any questions?
How does the flow model, the second approach that you presented, compare to graft in terms of efficiency?
So flow models are diffusion models. It's pre-training method. Graft is something you do on top of any trained model. So yeah, like I said, graft is not exactly related. Graft is a post-training method which can apply to any generative model. Right? Flow models is a way to do pre-training.
Understood.
Yeah.
Okay. Also, a question about the results that you presented for graft. You said that there were multiple steps at which we could estimate the variance of the rewards. I wanted to know at what level, so what was the granularity for the results that you presented on that particular slide?
Let me go back. Here or here?
The next one.
Yeah. So P graft can be done with 0.75. That is, you have n steps of denoising. Yeah. So I'll go and just train the. I'll only train from 0.1 n to 0.75 n. So k, if you go to this, let's say this is k. I train from n to k, right? Here k is equal to 0.75. Here k is equal to 0.5. Here is k is 0.25.
Understood. Yeah. Thank you.
Yeah.
Any questions?
Yeah, I had a question. Sorry. Yeah. So in the first part of the talk, when you discussed the problem of marginalizing out the basically the trajectories in order to get the KL divergence, right, between the sort of the trained distribution, the distribution you are training or parameterizing, and the original distribution. So essentially, you like you mentioned some problems wherein, if we just take the trajectory, full trajectory, and then take the KL versus, the actual term in the cost function, which requires a marginal, right? So I was just thinking that, this marginalization, it's not a question right now, but just, an idea or a comment, or maybe, it may be a future collaboration of idea. So basically that when we have when we are trying to take this trajectory and marginalizing it, the expression is very similar to path integrals, which we get in statistical physics. So I think, do you think there could be, or have people already tried some of the techniques, some of the approximation techniques, which...
So for example, you can do, there are importance sampling based methods. Right. So which you can use to get a unbiased estimator for the likelihood. Right. But it is computationally expensive. You have to do multiple rollouts and so on. The main problem is that log of this is not an unbiased estimator. You get a likelihood ratio, you can get an unbiased estimator, but log of this will be biased.
So those are based on those path integrals?
I don't know if it's based on path. I know it as importance sampling, but yeah, I don't know how it is connected to path integrals. Yeah.
Okay, and the second question I had regarding the flow based methods. So you mentioned that even after discretization, the mapping remains a reversible one, right? But I think just a small caveat would be that when you are in the discretized trajectory, when we are taking the reverse sort of steps, the derivative would be evaluated at the future step rather than the past step, right? So just that small difference could be there, right? In discretized.
So that's called the reverse Euler discretization. So if you have on the future, there's something called forward Euler, that is on the current step into discretize. There's something called implicit Euler or reverse Euler, where you discretize on the where you want to end up with. So that's, you have to solve an implicit equation there, right? So what I'm saying is the reverse Euler is the inverse of the forward Euler. Reverse Euler can be solved numerically under certain conditions, but you can't solve it with one step.
I see.
Yeah, so that's
okay, thanks.
So we're probably out of time, so one last question.
Hello.
Yeah. So if you go here, you can look at this graph. Okay, suppose what does this say? I've given you some partially denoised molecule structure, and then I want you to tell me the reward distribution of the fully denoised thing. Okay, if it was completely independent, it will look like this Bernoulli. Okay, I'll give it to you at after time steps 3 and over 4. Okay, it looks like this almost Bernoulli. You can't predict it. At n over 2, it looks like this has some predictability. It's visibly deviating from this. But if I look at it at n over 4, this is very different. So you have a lot of information about where you're going, whether you're going to be stable or not at time n over 4, but it's not available at these times. So that's the specific reason. You can almost see a phase transition of sorts here, right? So, yeah.
So yeah, we are. It's a great talk, Dheeraj, and as an appreciation, we have a small talk. Over to you, Ronak.
Yeah, okay. Is this on? Hi everyone, good afternoon, and thanks a lot for the opportunity to present some of our recent work here. So just to begin, I mean, this talk is going to be fairly applied because I work on fairly applied things. So just to let you know at the outset itself. And today I'll focus on some of our work on application of reinforcement learning to autonomous systems, specifically autonomous navigation. So to motivate this, as we can see, there's a lot of proliferation of autonomous systems in physical life recently, on the physical plane. So for example, we have doctors now who were initially or in the earlier days would actually be over the body performing operations. And they are now at a console somewhere else, teleoperating robotic arms for the surgery. Other examples are disaster response, where you have human operators deploying a team of maybe ground and aerial robots to do victim response, identification, etc. Then we have critical infrastructure inspection, for example, power lines, oil refineries, etc., where you again have human operators working with drones to investigate these critical assets. And finally, something that's very close to my heart personally is autonomous driving. So we have Waymo vehicles already driving on the road in select areas, and more soon to come, hopefully. So now, there are some challenges, right, with these autonomous systems, and here are two examples. So on the left, what you'll see is, let's see, yeah, you'll see a video from the urban challenge, DARPA urban challenge, where we have the MIT and the Cornell vehicle, who at this point are both trying to navigate further, and there is a crash at that exact location. Now, this problem you might think is a toy problem, right? It doesn't really apply to real life. What is the relevance for our daily life? Now, for that, let's take a look at this second video here, which is of a Waymo vehicle. So you'll see a Waymo vehicle on the right. It's trying to execute a merge into a busy highway. And as you will see soon, that it puts on the indicator lights on the left, and it tries to execute this merge into the highway. Now, the question here we should be asking is, as humans, we do this task every day. All of us drive, and we do this pretty simply, pretty easily. But you'll see here at this point that the Waymo vehicle is still waiting. It's still trying to execute this merge into the highway. And here is where the parallel to this video is evident. What you need to do here is you have to try and model how human vehicles will drive, or how humans behave, right? And there is a whole underlying sequential decision-making process that governs these kind of decisions. So the question here is, can we learn safe autonomous behavior, right, in navigation contexts? So now, just as a quick sort of contextualization of RL, all of you, of course, know this, but just to set the stage a bit. So we have, on the leftmost of the spectrum, we have retrieval-based models. On the right side, we have reasoning-based models. So the question is, where does RL fall in this spectrum? So you might have come across regression, nearest neighbors, or machine learning techniques, supervised learning techniques. They are very much retrieval-based models, right? So you train the model once, and then you just query at inference time, and you get an inference from these models. On the other hand, on the very edge of the spectrum, on the reasoning side, we have logic-based models. So here you can think of temporal logic, model checking, etc. And then a bit more towards retrieval, but highly reasoning also. is variable-based models, for example, Bayes nets. And then RL falls in the state-based models, right? So we have search and MDPs that govern these kind of state-based models. So the outline for today's talk is I'll first cover some of our work on learning without rewards. Now, why is this important or relevant to this setting is because in the driving context specifically, if you think about it, it's very hard for humans to articulate what is the reward function or cost function that we are trying to optimize. So can we deploy techniques from imitation learning or inverse RL to try and solve the driver modeling problem? Then we'll speak about safe RL. So the point here is that when you're trying to learn, let's say autonomously driving, you cannot go and break things while exploring the space, right? So how can we adapt safe RL techniques for autonomous driving? And finally, we'll talk about something that's a bit more, let's say, high level, meaning semantics. So for example, safe RL requires us to have safety constraints that are often human specified or programmed. But in, let's say, autonomous navigation for very cluttered environments, like indoor spaces or construction sites, it's very hard for us to write down those constraints by hand. So then, can we use vision language models or foundation models to provide that safety guidance to our RL agent? Right? So, okay, so let's begin. So, imitation learning and inverse RL. Yeah, question. So, VLM stands for Vision Language Model. For example, you might have Quen or Llama or GPT-5, which processes videos, for example, or images. Yeah. So, just to set this up, imitation learning and inverse RL, right? What are these things? So, for those of you who have seen this, hopefully it's a useful review, just a useful video, just to rock your memory. So, this first one is showing a baby. This is a research from neuroscientists and psychology, where the researcher is showing the baby a certain action. And very promptly, the baby imitates that same thing. So, this goes to show that imitation is a fundamental way in which us humans learn, right? On the other hand, in this second video, we are seeing another experiment where the researcher is trying to perform this task. He wants to put some objects into a cupboard, and the agent is the baby here again, okay? And after a while, we see that the baby is able to go and open this cupboard, meaning that in some cases, we humans are able to uncover what is the goal or the reward function that that the agent has to follow, right? So on the left side motivates or gives us imitation learning, and the right side gives us inverse reinforcement learning, where you try to uncover the reward function and then do RL based on that reward function. So, and here are some applications of the same. So on the left, we have the Alvin system, which was the first imitation learning using autonomous driving system based out of CMU, I think. So here is a vehicle that is being completely driven without any active human driving, and it's driving on campus roads. So this was the first example of a deep neural network, not very deep, but deep for those times, used to do self-driving vehicles. And on this side is again an example of imitation learning, where is the famous robot ball in a cup task. So the demonstrator is showing the robot, okay, what is the motion you should follow to get this ball to come into the cup. And the challenge here, if you think about it, is again the challenge of cost functions or reward functions. It's very hard for us to specify to the robot at what point, what is the cost function that you're trying to optimize. So therefore, learning from demonstration becomes a much easier prospect in such settings. Okay, so to come back to our, let's say, setup of trying to model human driving, yes? So you said that second video was an inverse RL. Yeah. Elaborate, why do you say it's inverse RL? In the previous slide, right? Yeah. Yes. So the question is, why do you call this second video? Oops, sorry, hope I can play it. Okay. Maybe play it from here. So why do you call it inverse RL as opposed to, let's say, imitation learning, right? So in imitation learning, what you would have required to do is you would have had to show the agent, i.e. the child, the exact action as to go here, open the cupboard and come back. Whereas in IRL, the child is somehow inferring that the agent wants to open this cupboard to get some reward, right? So that is the key distinction here. Instead of trying to demonstrate the whole trajectory to the agent, can you just provide it some examples from which it infers what the reward function is and then goes and solves the task?
I mean, I wanted to say it it is clear that it's not imitation learning, but it's not clear whether it is inverse RL. That is not obvious to me.
Okay. No, that's a very good, point well taken. I mean, my goal here is to illustrate what the underlying theory or the idea behind IRL should be. But yes, we don't know whether the child is trying to actually formulate a reward function in his head. Yeah, good point. Okay, so yeah, to come back to our setup here, what are we trying to do? We're trying to basically get a mapping from a state, i.e. a situation on the road, to an action, which is an acceleration and a steering command in this case. So what might we do? We might basically try and, let's say, record some data, and these are actually open source driving data sets. So on the right, we have the US 101 highway NGSIM data set. On the left, we have HIDI from German highways, right? So recorded using a drone. And you might say that, okay, let's just take this and do imitation learning on it, right? And what is the elementary school imitation learning method? It's basically behavior cloning. So take these state action pairs and try and learn a regression between those states to actions. So when we try that, what happens is shown on the right here. All the blue vehicles are driven by our behavior cloning trained agent. Red shows collision and yellow shows off-the-road driving. So as you can see here, things are not good at all, right? Things start going haywire, okay? So behavior cloning, as you can already maybe guess the reason, it's because of cascading errors, right? So the moment your vehicle goes to a state which is not in the demonstration data set, it makes an error, and then those errors compound over time, okay? So how did we approach this, this problem? So we tried two approaches. And I'll speak about both of them briefly. So the first one is a model-based approach. So wherein what we're saying is that can we try and use underlying models of the vehicle dynamics, which are parametric models, and try and learn what those parameters are. That's the first one. And the second one is a purely model-free approach, where we'll try and do inverse reinforcement learning for this task. Okay? So hope the setup is clear. Okay. So approach one, model-based, these are basically driver models that have been given to us from, let's say, mechanical engineers who work on this. And this is called the intelligent driver model. So it basically relies on a set of parameters. So let's say, what is the minimum spacing you might prefer with the vehicle in front of you? What is the max acceleration or the max deceleration you might prefer? And what is the desired speed you might prefer? So these are basically preferences which govern how people might drive. So an aggressive driver might have very low values for d-min, right? And a more sort of conservative driver will have very high values for that parameter d-min. So then what we do is we take these models and we sample an action from a Gaussian centered around this A sub IDM, which is the model output, okay? And now our goal is to try and uncover what these parameters are from data. So data in this case means we have some position data and velocity data of the vehicles from the data set, right? So can we use those sequences to uncover these parameters? So we're trying to find a distribution P theta sub t given a sequence y1 through y capital T, right? So theta here represents the parameters and theta sub capital T is the parameter sitting at the end of the sequence, right? So we observe t capital time steps and then find what is the distribution over theta t. That's the problem, okay? So now how might you approach this, right? You might try and think of some kind of recursive Bayesian estimation technique to solve this problem, right? So what we said is let's try and utilize the biggest hammer there is, which is particle filtering, right? So here's how it works. This is just illustrative purposes. We have a two-dimensional parameter space, let's say. So this is a bucket of particles with two parameters, theta 1, theta 2, for example. And every point here, every particle here represents a setting of the parameters. So this is the green vehicle we are trying to model, and what we have is data from the data set. So the red vehicles are surrounding vehicles. And we basically try out, let's say, one step forward in time based on a certain parameter setting here, so circled in blue here. And based on that, we get a Gaussian where the vehicle might end up in our simulation. And then we have, this is the prediction step, and then we have the correction step where we have the ground truth data from the data set, shown in green in this case. And using that, we reweight the particles accordingly based on the ground truth from the data set. So that's a very sort of quick overview of how particle filtering works in this case to try and uncover what is the parameter values for the underlying driver models, okay? And here is a video that shows this in action. So what you'll see here is in the white, you'll see the ground truth. demonstration data. And in the blue, you will see what is our model driving doing in this case. So if there is good overlap between white and blue, it means that the model is able to learn something via particle filtering. Yes?
What do the particles here represent?
Right. So the question is, what do the particles represent? So if you go back here, we have this 7-dimensional parameter space here. So each particle represents 7 different values of those parameters. Right. So here is a video. So we see that there is an overtaking scenario here, and the white and the blue seem to overlap to a fair extent, meaning that we are able to capture the underlying parameters of the driving behavior via this particle filtering approach. Now, of course, there is a big caveat here. The caveat is that this approach needs a model. And what was the model in this case? It was the intelligent driver model, IDM, right? And that model only works well for these situations, right? Where you have very straight roads and you can model them using these 7 parameters. So, which is why you know what's coming next. What's coming next is that we can go for a model-free approach as well. So that's where inverse reinforcement learning comes into the picture, right? This was a model-based approach where we said, can we do parameter estimation? So like system identification in robotics. And next we go for inverse RL as the second approach to the same problem. Okay, so as a quick recap, the idea in inverse RL is, can we try and find a policy pi, a policy pi which incurs in expectation less than or equal to the cost incurred by the expert demonstrator, right? So pi E here stands for the expert policy. In this case, human drivers. So now the issue, of course, is that we don't know what the underlying true cost function C true is, right? If we knew that, there is no need for inverse RL at all. We can just do RL, right? So now, how do we impose or how do we go forward given this requirement or this goal? So what we say is that, can we impose this condition for all possible cost functions, all C in some class mathcal C, right? So the cost functions live in some class mathcal C, and we impose this condition for every possible cost function C in that class. Okay. So now how do we try and approach this? What we say is that, what is the worst possible cost function I might have in this class? So the worst possible cost function is basically a maximum over all possible cost functions in this class of the difference between the expectation incurred by our agent pi and that incurred by the expert demonstrator pi sub E. Okay. So then if you can find this worst possible cost function C worst, then you can find the policy. So how do you find the policy? You basically say, I'm going to do an argmin over the expected cumulative cost I get using the C worst in this case. So therefore what we end up with is a min-max problem where we have this expectation over the expectation of cost incurred by the agent minus that incurred by the expert demonstrator, minimum over the policy set and maximum over the cost function class. Yes?
Here is C same as the Q function?
So the question is C the same as the Q function? No. So in this case, C, you should think of C as the reward function, right? This is just the cost-based formulation. So C is basically the per step cost in this case. So it's a function of state action. And then what you can do is, using that you can build up the Q function. So the question is the max over C over both the terms? Yes, it is over both the terms. Yeah. Right. So the technique we use to try and attack this problem is, or before going there, existing approaches basically said that, can we use some kind of featureized representation of the state space to try and tackle this problem? So you would have come across Abil and Ang's paper, for example. So those basically have the restriction that whatever the cost function is beyond that class of mathcal C. If the cost does not lie in that mathcal C class, then those methods will not work. So therefore, what we need is something more powerful, and what we use in this case is something called generative adversarial imitation learning, right? So here what we have is the standard GANs-based approach, where the policy pi generates a sample. In this case, it generates a sequence of state action pairs. The discriminator basically says, is this real or fake? And then outputs a binary value. And then this loop continues, and via this route, we basically solve the problem posed in the previous slide. Okay? So the benefit of this approach is there is no need to hand specify basis cost functions, which is what prior approaches did. And also, crucially, it allows policy gradient based approaches. So prior approaches use value function based methods. Via this, you can basically use policy gradient based approaches. So what did we use? We basically used a policy which was a recurrent neural network. So RNN, because in this driving case, often you have partial observability, right? You won't be able to see what the exact state is. And the second thing is that the policy outputs the mean of a Gaussian over action. So you need stochastic actions for these methods to work, which is why the second point matters here. And then we have a TRPO update for the policy optimization part of things. And we have an ADAM update for the discriminator. Right? So we train both the policy and the discriminator simultaneously via these approaches. Okay? So, and what are the features needed for this? So here is something that's a bit more specific to autonomous driving itself, which is that we need these kind of features, right? So we need to know what the ego vehicle is doing. We need to know what the leading vehicle in front is doing. And we need to have some kind of representation of the state itself. So we have LiDAR-like measurements here, range and range rate. And we also have some additional things we provide the agent, which is sort of reward shaping, right? Which is what we provide as domain designers of this problem. Okay, so how did this basically work? How did this do? So on the right, we have a plot of the distribution over the speed of the various traffic entities in this context. The black is the ground truth. And in green, we are showing our method. And in orange is the baseline method. So what we can see here is the distribution over speeds we get based on this method is quite close to the underlying ground truth distribution, visually at least. And then here is a video showing how the vehicles now do based on IRL-based trained policies. So all the blue vehicles are driven by these policies. And as you can see, these are fairly well behaved as compared to what we saw in the behavior cloning approach. Now, of course, there is a caveat here. I should mention this is quite a cherry-picked video, right? It's not always this good. And we are still trying things out to make it work better in general cases. Okay? So with that, I'll stop here for any questions on this part before jumping to the next part of the discussion. Okay, so if not, let's now switch gears a bit and talk about safe reinforcement learning. Right? So the context is, in this part, we spoke about how can we try and model how humans drive vehicles. And the safety question there was, if your autonomous vehicle has to drive in human roads, it better model how humans may drive around it. And here the RL part was that can we use RL techniques like imitation learning or inverse RL to try and model human driving behavior. The next question now becomes, okay, can we train autonomous agents themselves to drive well on these roads, right? So take a step back. So this work is led by my master student Mahesh Keswani, and it's on safety representations for reinforcement learning. So let's jump into it. So just a quick recap for those of you who are aware of RL and safe RL, and hopefully review for those who already know this. So we have examples like these, which is RL, right? We have the breakout game, which is basically pure RL. Here you have to try and maximize some expected reward value. Other examples are emergence of locomotion, right? So we have agents which are trying to learn how to walk. Again, there is a very clear reward function. You have to try and maximize expected reward function. But think about this example here. So this is from NVIDIA, and this is a video of when they were trying to train autonomous vehicles, autonomous driving on the road. So here is the NVIDIA vehicle. It's undergoing training right now. And what we'll see is, in a bit, things like this, right? In training, it is going and basically knocking over cones, breaking things, driving on the grass, narrow misses, etc. Right? So how do we think about this? Right? We can't just have the vehicle try very unsafe exploratory actions in training. So therefore, there is something called safe RL. So if I go to the next slide. Yeah. So in safe RL, the context is a bit different. You have to still maximize expected reward, but you have to also satisfy a constraint on the cost. So in this example here, this is from the safety gymnasium. You have a robot, a RC car robot. It has to get to a green goal location, but if it enters any of these blue regions or these green boxes, it incurs a cost, right? And there is a constraint on how much cost it can incur in expectation. And we'll formalize this a bit subsequently. Okay. And here's an example of the half cheetah learning to walk. So as it walks, the constraint is that if it exceeds a certain velocity value, then there is a cost given to it. So all the red you see here is when the cheetah is going beyond a certain velocity limit. Okay. So the point here is that cheetah can't just keep going fast and faster and faster and thus break its own joints. It has to basically be under a certain velocity value. Okay. Right. So just to formalize this a bit more, here is the standard picture of RL. So there is an agent in an environment, takes an action, gets a reward in the next state. And it's defined as a tuple SA, T, R, D, and gamma. And the goal is to try and maximize this J of pi, right? So expected cumulative sum of the rewards with the first initial state sampled from some distribution D of S. In the safe RL context, the formulation is slightly different. What we have here is we have the RL constructs as well as a few additional things. So we have C, which is a cost function, and we have beta, which is a cost limit. So now the goal is, can we try and find pi star, which is argmax of J pi over a set pi C, where pi C is a set of feasible policies. Now what does that mean? It means that my policy pi in expectation incurs a cost less than equal to the cost limit beta. So this is called the constrained MDP formulation, and this was pioneered by some of the eminent speakers in this workshop itself. Okay. So here is the definition of JC pi. So now what you'll see also in the literature is formulations like this, where you try and basically learn now a cost critic. So you have come across reward critics, which is Q values predictors. What we have to now also learn is cost critics. So this basically predicts Q pi SA of the cost. So Q sub C pi of SA. So it's the expectation of sum over discounted costs starting from state S and taking action A. Okay. So now the question becomes, okay, how can we try and solve these? And I won't go into the details or a review of safe RL here, but existing methods, the issue that they have faced is that something called primacy bias, meaning that if they encounter difficult situations at the beginning of training, then they result in very conservative behaviors being learned. So they stop exploring, right? So what we have now is we have recent work which says that, this is from Money et al., which talks about how can we think about safety in this context. So I'll I'll go through an example to describe this a bit more. So this is the Island World test bed from Like et al. What you have here is you have a maze, right? And the agent is shown in light blue and the goal is shown in green. And this maze has these water cells as well. So if you enter the water cells, you incur a cost. And the goal is for the agent to get to the goal state G. So it gets a reward for going to the goal state G and incurs a cost for entering these water cells. Okay. So now what they have found is, they have found that if you provide some underlying safety information to the state itself, then the performance gets better. So what does that mean? It means that in this case, can you tell the agent how far away it is from the cost cells? So here are some examples or results from this study. So they compared DQN with ground truth risk, which I'll describe in a bit, which is a safety information provision. And then they had two methods which basically model uncertainty. So C51 models the uncertainty, and Bootstrap DQN also models the uncertainty in different ways. What they found is in these cases, your DQN with ground truth risk gets a much higher return, also incurs much lesser cost as compared to vanilla DQN and the other methods, C51 and Bootstrap DQN. And now if you look at the Q values, that is very interesting in this context. So in this picture, we are seeing on the X we have episodes, on the Y we have Q values. The top one shows the Q values for the vanilla DQN, and the bottom shows the Q values for DQN with GT safety, ground truth safety. So ground truth safety in this case is basically saying that I'm going to just provide the state with how many cells away it is from the water cells. Okay. So here what we see is that as you evolve, as the training evolves, in DQN, all the three kind of GT safety values are clustered together. The Q values for all of them are clustered together. So the agent is not able to distinguish between which cells are more unsafe than other cells. Okay. Further, if you look at the Q values, they are all very low compared to Q values with the ground truth safety given, right? So this shows that the agent is becoming very, very conservative. On the bottom, you're finding that the Q values are much higher, firstly, and the second thing is that as you evolve, you find that the blue dots all get lesser Q values. So those states which are basically closer to the water cells get lesser Q values. So providing ground truth safety helps the agent in trying to learn safe behaviors. That is the whole takeaway message from this. Okay. And another very interesting thing that is found is you have the state on the x-axis and the state visitation count on the y-axis. With vanilla DQN, what you find is that the agent just stays close to the initial state. It doesn't explore much at all. So again, showing that it learns very conservative behaviors. And with DQN with ground truth safety, what you find is that the distribution of visitation is much more widespread than compared to the vanilla DQN one. Okay. So this method is called safety representations for reinforcement learning, SRPL. So now what we'll talk about is what has been done to do safety representation for autonomous driving specifically. So we'll go there next, and then we'll see how we can use this method in autonomous driving and what the results show in that case. Okay. Okay. So here are some methods that have been used for safe RL autonomous driving. So first we have something called LAGU, which is basically trying to model epistemic uncertainty for the reward critics for safer exploration. So what you do here is that you basically say that I'm going to have an off-policy safe RL base, right? So in this case, it's SAC Lagrangian. And then it just demonstrates this idea in synthetic experiments, so in meta-driven environment. Then we have scenario net, which is basically trying to use standard RL in real-world data sets. So Waymo is a real-world data set as compared to meta-drive, which is a synthetic environment. And then this paper basically says that how can we use WOMD for RL and not for safe RL? It was only for pure vanilla RL. Then we have something called GOLD, which is fairly recent, which says, can we do offline RL plus online distillation to learn safe behaviors? So here the underlying backbone was decision transformer, and then they used some online distillation to make the agent learn better, right? And then we have our work, which basically says, can we use this idea of safety representations and combine those with existing base algorithms to try and demonstrate how it works on real-world data sets. So again, as compared to existing work, our work is on real data, which is WOMD and NewPlan. And I'll talk about this data subsequently. Okay. All right. So now one more question is what has been done in the literature to represent safety at the outset? So we have many different ways. One at the bottom is what we just spoke about right now, which is that can we augment the state with some kind of predictive notion of safety, right? How far away are you from the constraining cells? And other approaches basically have tried things like uncertainty-based methods. So you say that wherever you're uncertain about the state space, you explore less in those regions. You have direct action filtering. So basically you say that can you filter out some actions at the outset given a certain safety notion of those actions. And you have some kind of augmentation of state as well, which is what SRPL builds on. But these were basically just scalar values trying to somehow characterize how far away the state is from unsafe things happening. So what we'll see next is how does actually SRPL deal with that issue, and how does it give us a richer representation of what safety is and how far away the unsafe states are. Okay. So it's something called the steps to cost model. So the SRPL learns the steps to cost model, meaning can we predict how far away unsafe states are. So what we have is a mapping from state to a simplex over the horizon HS. So let's think that we are thinking of HS steps further in time, and this is of course much less than the horizon H. Okay. And then what we're trying to learn here is the probability of incurring cost in T time steps. So G sub T of S learns the probability value of incurring cost in T time steps exactly. So for learning this, we have to basically have a replay buffer. Now here there is a caveat, which is that if the base algorithm is already, if it's off policy, then you have a replay buffer available to you. But if it's on policy, then you have to create a replay buffer separately for this idea to work. So what does the replay buffer store? It stores states and steps to cost. So how far away are you to an uncertain, to a risky state from a certain state S0 or Sn, let's say. So this gives you a labeled data set of how far away every state is from the unsafe things happening. And then you train this via max log likelihood. Okay? So that is the idea of trying to learn predictive safety representations of how far away I am from a certain unsafe state. Okay. So this is the S2C model. How does it work as an example? So let's say we have these 5 states that we are thinking about. A horizon is 4. And we have unsafe things. So S1 and S3 are the unsafe states in this case. Now we initialize this S2C model with the value of 4, let's say in the beginning. And then we find that, okay, for the last state S4, I'm not sure how far away I am from the unsafe things happening. So let's keep the value at 4. For S3, the unsafe thing is happening at that state itself. So the value becomes 0, 1 for S2, 0 for S1, and 1 for S0. Okay? And then what we do is to make the distribution learning more tractable, we quantize these values. So let's say we only quantize them to having value 0, 1, and 2. So therefore, this value takes the value 2, and everything else stays at the value 0. Okay? So that is how you will provide the data for training the S2C model. Okay? All right. So here is an example in the same water world of like et al. So there is the agent, there is the goal G and water cells here. And what we are seeing here is the S2C model, what it has learned. So the probability of being in an unsafe state in number of steps is what is being shown here. So as we can see here, the RSB has a much skewed distribution towards lower values because B is close to the water cell here, whereas SA is more uniform. Yeah, yes. Yeah, the question is, what does the 4 represent here in this case? So in this case, since you only have 0, 1, 2, 3, 4 steps, horizon steps, the initialization you're giving to the S2C model is a value of 4 because it can't go beyond 4. So the question is, why does S4 again have 4 in the next step? It's because from S4 you don't know how far away you are to the unsafe things happening. So initialize it to the maximum possible value. Okay. So this is a picture showing how this whole thing works and how we integrate S2C with the safe RL methods. So what we have here is the environment and an action being taken by an agent. And this gives us a trajectory buffer, right? So if you're doing one policy method, you need to create the buffer separately. And then based on this buffer, what you are learning is the steps to cost model, S new. And you're training this using negative log likelihood, as we just mentioned. And here in the blue, we're basically seeing the usual RL approach happening. So this is the RL piece, this is the steps to cost piece. Right? So red S2C training, blue is the RL agent, and green is the agent itself, and blue is the RL training happening. Okay? So what we'll see next is how do we adapt this whole idea into the autonomous driving, real world driving dataset context. Okay. So what we have is we have datasets like Waymo and NewPlan. Waymo is from Google, NewPlan is from Meta. And basically, these datasets have these kind of characteristics, right? So Waymo has a track length of about 136.55 meter, number of vehicles, pedestrians, intersection ratio, etc., etc. So this shows the diversity of the dataset that we are using. And the key point here is that prior work has not addressed these challenges in real world driving datasets usually. They have usually worked with synthetic datasets only. So the next question is, how do we use static data? Because these are actually recordings of vehicles, right? These are just, we only have recordings of these things. How can we use that to make simulators? That's the next question that we're asking. Because to train an RL agent, you have to basically simulate in the real world, right? You have to try and simulate in some simulator the impact of actions that are being taken, what happens. So we take this synthetic data and convert it to simulators via ScenarioNet. So here is the Waymo dataset, for example. We convert it to a unified format, and then you can use this for single agent learning, multi-agent learning, and also scenario generation, right? And this third piece is important for us because we are trying to basically generate scenarios for the agent itself to try and simulate and learn from, right? But the point is that this scenario net can basically be used for many different kinds of learning as you might prefer. Okay. So now the question is, okay, in the real world driving, what is the state? So the state is the following. So we basically have a 50-meter range of environmental perception, right? So think of if you have a vehicle, you will mount it with LiDAR sensors or cameras. So in this case, what you have is a 120-dimensional vector for LiDAR-like observations and 12-dimensional vector for drivable area boundaries, right? So you provide this information to the vehicle via these sensors. Then we have vehicle state and navigation guidance. So vehicle state would be the ego vehicle velocity, distance to the vehicle in front, and navigation guidance would be where does the vehicle have to go eventually and what are the waypoints in the interim of the vehicle. Okay. So now sort of wrapping this whole thing together, how does this actually work? So we have the state S sub T, which is LiDAR plus other things that I just mentioned. We have a policy pi, which is driving the vehicle in this environment, which this policy gives acceleration and steering commands. And this goes into MetaDrive, which is a simulation environment that we're using in this case. And then MetaDrive outputs the next state S sub T plus 1 using scenario net simulation generation capabilities. Okay? So that is the whole sort of pipeline of how this is deployed in autonomous driving context. So the reward function and the cost function, right? So to bring us back to safe RL, we need both R and we need S to specify this problem. So the reward function is basically a function of how far are you progressing on the road and what is your heading and what is your lateral heading as well, right? So we have various constants here from the literature in autonomous driving. And the cost function is basically penalizing two things. If you crash and if you go out of the road, you're penalized accordingly. Okay? So of course, the point here is that try and make progress on the road while incurring or while staying under a certain constraint limit given by this cost function. Okay? So here is the entire, let's say, pipeline. We have the WOMD datasets. We convert to a state, and then the blue here shows the baseline safe RL algorithm, right? So which is, think about, let's say, CPO or on CRPO or P3O or any such algorithm you like. And then the green portion is basically the SRPL framework. So eventually SRPL, what it does, it says that I'm going to augment my state with a safety representation as well. So the steps to cost model is augmented to the state directly. And that is what the agent processes as it learns in the RL learning progress. Okay? So here is the algorithm. We can skip this. You get the idea. And here are some training curves showing how SRPL augmentation, how does it work in this context. So in the top, we have the base algorithms. On the left, we have the reward, and on the right, we have the incurred cost, both averaged over 5 different seeds. In the bottom, we have the SRPL augmented algorithms, right? So SRPL, CPO, SRPL on CRPO, etc., etc. Now, the few key takeaways here is that there is a much steeper learning when you augment with SRPL. So in the bottom curve, you can see a much steeper learning, which means that the sample efficiency is much better. The second one is that algorithms like on CRPO, which is in the light green, show very high variability in terms of the cost function. Whereas augmenting with the safety representations helps it become less variable in the cost satisfaction. And then finally, and we'll talk about evaluations a bit more, is that we find that with SRPL augmentation, we have better cost satisfaction as compared to the baseline algorithms. So as we expected, and as was promised in the toy environments, SRPL does help, and we see this also holding true in real-world autonomous driving case study. Okay. So here are some evaluations. What we have is 2 data sets, WOMD and new plan. So again, real world. And the metrics are given here. So this is reward, cost, route completion, success rate, and out of the road. Right? So higher reward is better, higher route completion is better, higher success rate is better, etc. So here is the expert values. So what do humans do in terms of these metrics are shown here. Then we have the non-SRPL algorithms. So we checked 5 algorithms here: CPO, PPO lag, TRPO, PID, on CRPO, and P3O. So we won't cover the algorithms here, but you can go back and take a look at how these work on your own time. And then here are the SRPL augmented versions of these safe RL algorithms. So what we find is that we find a higher success rate, which is shown in bold in many of these SRPL augmented cases. And we also find that improvements for the cost satisfaction as well, as compared to non-SRPL baselines. Okay. Now there's one more interesting thing here, which is that the SRPL also helps us transfer across data sets. So what we're testing here is, if you train on new plan and deploy on WOMD versus train on WOMD and deploy on new plan, how is the performance, how is the agent performing? Okay. So what we find is that when you train on WOMD and go to new plan, the agent performs much better than training purely on new plan itself. This is actually quite surprising for us. And why is that? We'll discuss that a bit further down the line. Okay, so what are the key findings, just to summarize from these experiments? One is that the SRPL reduces the cost in 4 out of 5 algorithms on WOMD and 3 out of 5 on new plan. Okay. It also improves the success rate in 4 out of 5 algorithms. And the effectiveness is a bit variable by data set, right? It's not good across all data sets. So there is a question there as to why is it better on certain data sets as compared to others, which we have to still answer. And what we have found is that for SRPL P3O, which is the best algorithm in terms of cost and success rate on both data sets. Okay. So P3O seems to benefit the most from SRPL augmentation in this case. And here are some more findings on the transfer aspect of it, which is that if you go from new plan to WOMD, it's worse generalization. If you go from WOMD to new plan instead, it's doing much better. And we'll talk about this a bit. And then SRPL versus non-SRPL, that's quite clear. So if you have SRPL, it improves much better cross-domain performance as compared to non-SRPL algorithms. Okay. So the next question we have is basically a specific question on safety. So this was kind of overall aggregate results on the data sets. Next, we looked at specific safety scenarios, meaning what? So the first one is that we have vehicle density. So this comes back to the question about why is it better when it transforms from WOMD to new plan and not the other way around. It's because WOMD has higher vehicle density situations. So as you can see here, what we have here is we have different scenarios with different density of vehicles in those scenarios. And on the left, in this part, we are showing the baseline average cost and average SRPL cost. And we find that the reduction is quite significant in the high vehicle density case. What does that mean? It means that if you have more vehicle density, you have more possible interactions, right? Possibility of more constraint violations. So there, SRPL performs much better and gives us much more benefits. And it turns out that WOMD has much more higher vehicle density situation as compared to new plan, which is why the transfer is explained, right? And the second thing we thought about is, okay, can we go and look at specific safety scenarios in these data sets? So what we looked at is 251 scenarios from the WOMD validation data set, where more than 3 base algorithms exceeded the cost limit. Right? So these are basically very unsafe situations where the base algorithms like CPO, TRPO, PID, etc. went beyond the cost limit. And we look specifically at how does SRPL provide in those specific scenarios and what improvements it provides us. So we found here is that an improvement of almost 50% over the baselines via SRPL in those specific situations, and an improvement of 32%, for example, for TRPO, PID in the success rate as well. Right? So this shows that if you look at not just the aggregate, but also specific safety scenarios, SRPL seems to provide much more benefit when augmented with the underlying base safe algorithms. Okay, thanks. Okay, so how have the algorithms done? Let's look at some videos for this. So here is what we'll see here is we'll see an example from WOMD, and this is TRPO PID on WOMD. So here you have a vehicle that is approaching, and your TRPO PID agent goes almost and crashes here with the vehicle in front. On the bottom, we'll see how SRPL TRPO does on this SRPL TRPO PID. So we have the vehicle coming here and comes to a stop, lets the vehicle pass, and then goes ahead. So it shows that, okay, with SRPL, TRPO, PID is learning better safety behavior, as shown from this one video. Again, caveat is that it's cherry picked. It's not this across the board. Okay. Now here is an example of the transfer aspect I spoke about. So on the top, we'll see SRPL CPO trained on new plan itself and deployed on new plan. So here is what it does. So you'll see quite shaky behavior, and you'll see that the route completion is not very high. On the other hand, on the bottom, we have SRPL CPO trained on WOMD, but deployed on new plan. So there's a transfer aspect that I spoke about. And here you'll find that the vehicle is covering much more ground. The behavior is still kind of shaky, slightly less shakier, but it's covering much more ground as compared to trained on new plan itself. So again, what we see here is that if you have more diversity in training, which WOMD has, your agent learns better and performs better with SRPL augmentation. Okay. However, the caveat to mention here is that it's not always so good, right? So CPO seems to be the one that suffers the most or does not benefit equally from SRPL augmentation. What we have here is CPO WOMD trained deployed on WOMD itself. Here is how it behaves. Here is the turning happening here. And here is SRPL CPO on WOMD itself. So what you'll see here is not such good behavior, which means that this SRPL benefit is not across the board. There is still more work to be done, specifically on CPO. So the question now becomes, why is CPO not benefiting as much from SRPL? We're thinking about this right now. Okay. And now there is another thing that basically is surprising to us, which is the fact about robustness. So if you think of autonomous driving, what you'll think is it has to be robust. So for example, sensors might have rain-induced distortion. You might have fog. You might have lighting change in tunnels or lens flare. And what we found surprisingly is SRPL augmented algorithms also give us robustness. So how do we see this? So what we are showing here is on the x-axis, we have the noise level corruption, adding it to the state. So in this case, we have a Gaussian noise added to the LiDAR measurements. And the left plot shows the reward and the right plot shows the cost. The solid lines show SRPL augmented methods and the dashed lines show the underlying base algorithms. What we find here is that with the cost corruption increasing, our SRPL augmented methods still satisfy the cost constraints. On the left, what we find is that with the to a certain extent of noise corruption, the SRPL methods perform better and get more reward than the non-SRPL baseline methods as well. So now the question we are thinking about is, okay, why is SRPL giving us robustness as a byproduct? So we need to think about this a bit more. Okay, so I think I have about 5 minutes more. I'll quickly conclude by presenting this final piece here, which is on vision language models and safety guidance from those vision language models. So this work led by my student Abel, jointly with Professor Rohan Paul, who is the co-advisor here. So here, so the backstory here is, the motivation here is that so far we've spoken about autonomous driving only, which is a very structured and very sort of, let's say, well-defined navigation problem. But the question you'll say is, hey Ronak, it works for well-structured, but what do you do if you go for more unstructured navigation problems, like indoor navigation, like on the road, like cluttered areas, etc. Right? So what do you do there? So for example, you might have things like your robot is navigating and there is someone who is putting a barrel across your path, or someone who's driving a robot across your path, right? So what do you do in those situations? Or you might have a puddle on the road, like here. So this is basically a very difficult thing for us to quantify via cost function. It's a very semantic notion of safety, right? You have to understand that a puddle might be unsafe to go over. Another example could be a reversing car. Again, very hard to specify via constraints. You have to basically understand that this reverse light semantically means that the car might be coming back. Okay? So the question we have is then, how can we try and learn safety for robot navigation in dynamic unstructured environments? Okay, like a puddle or like a hazard sign in this case, right? So how do we pick an action that is semantically safe in these contexts? So what we do here is we follow the approach followed by Pivot, etc., recent papers that basically provide some kind of action encoding or an action prompt into the image itself. So here we have 3 possible actions that the robot could take, and the question becomes, can you give me a ranking over safety for these 3 different actions? Okay? So you have observations, which is what the robot is seeing, you have action encoding. There is some function F safety, which gives us sigma over A sub m, right? So A is the action, sigma is the ranking over safety over these actions, okay? So the question is now, can VLMs approximate this ranking function informing an agent's belief state for downstream planning, right? So here you can't do constraints or safe RL very easily. Can we leverage the help of some foundation models to provide safety guidance to our agents? That is the premise here. So I'll quickly sort of skip over this. So what we have is a data set gathered over 2 months in the IIT Delhi campus in various locations. So for example, sprinklers on the ground, reversing cars, construction sites, cyclists, etc. So we've gathered some data using this platform here, which has a camera mounted on top. And we have diverse scenarios in illumination, right? So this data set is basically kind of a safety specific data set that we have gathered on campus settings. So, and we have different categories, so collision, hazard, motion forecasting, traversability, etc. And here is a tool we have built, which basically helps us query different vision language models like GPT-5, Gemini, GPT-5 Nano, etc. And gives us a chain of thought kind of reasoning as to what the safety rankings are and why it gave those rankings to us. So the problem here is basically this, that you have this robot, it proposes 5 different actions via action encoding, and the VLM has to give us, okay, what is your safety ranking on these actions? So how does the VLM do, right, off the bat? So here is 2 examples, here are 2 examples where the VLM does quite well. So here the green is basically, not the green, but the orange here is where the VLM says you should go, okay? So it's saying the right thing to us basically, right? But a VLM does not do well in these situations. So if the barrel is rolling across you, the VLM says you should still go there, which is completely wrong, right? You should not be going there. And here is a sprinkler, again the VLM says go into the water, again completely wrong. So what we have been working on is basically a visual prompting strategy, for example, semantic segmentation, grids, set of mark prompting, etc., to get safety information from VLMs in a structured way. So I'm out of time here, I'll just quickly conclude in the last minute I have by summarizing. So let's see if I can go to that section. Yeah. So what we basically spoke about is safe RL and how can we do safe representation augmented safe RL, which showed that we can get better sample efficiency, we can learn constraints, and also uncertainty estimation, right? So these are, of course, ongoing projects, ongoing work. And we also try to do safety guidance from visual language models, which will help us down the line in motion forecasting, or maybe hierarchical planning and deployment as well. So the picture I wanted you to take away basically is that imagine a robot in a hospital setting. It's trying to help nurses and doctors. It has to be safe. It has to also get high reward, right? So safe RL is paramount here, and safety guidance also is paramount in this context. Right, we can skip this, and just to sort of finally tell you what we're doing in the group, we're basically thinking of this picture from Russell and Norvig, right? We're thinking of agents with humans, and how can the agent basically work in the real world? And this gives us multiple themes. So we work on robotics, autonomous control systems, multi-agent learning, human-AI interaction, and of course use RL and imitation learning as sort of underlying tools for the research we do. And with that, I'll stop here. Thanks for your attention, and thanks for the opportunity again. I'll take any questions. Thank you.
Hello. Yeah.
This is.
Yeah. Hello. Yeah. Thanks for the talk. So just a high-level question, like how is this approach different from social learning related frameworks where an agent can learn from the actions of others? So is there any kind of work in using the social learning frameworks studied in this particular domain?
Right.
Because it has a lot of agents and experts. So I can also learn from the actions of the experts.
Right, so I haven't come across the term social learning myself. By social learning, can you just tell me a bit more about what you're...
Just learning from the actions of others. Like something I think IRL can be used as a tool.
Yeah.
Instead of learning the rewards, I'm just seeing what they are doing and then do some sort of imitation.
Yeah, absolutely. So I think what you're describing is imitation learning, right? You're saying that if I have demonstrations from experts, can I use that directly to learn a mapping from state to action? That is called behavior cloning. Now that has not worked in the past very well, but is now showing a lot of promise. For example, the OpenX embodiment dataset or RTX1, etc., or the physical intelligence PI model. They all use behavior cloning because diffusion models have now become so strong that they make very few errors to begin with. So the cascading errors can somehow now be done away with because of this diffusion models. That is one. The second is social learning. I think when you say social learning, I also thought about social navigation. So for the last part where I spoke about vision language model guidance, there is very interesting work from Dinesh Manocha's lab, which is called social VLM. So there you're saying that can VLMs give us a social cost? So when as humans we navigate in human spaces, we have a notion of socially acceptable navigation. So that's also a very interesting area of work where the VLMs can give you social cost, and then you embed that into a dynamic window approach kind of planner to do motion planning. Yeah.
The reason for connecting to the social learning is I think some economists have studied in social learning there are some drawbacks of herding and information cascading, where everybody is rational but still as a collective behavior they kind of go to a suboptimal space, like maybe some unsafe in this region.
Mm-hmm.
So I was like kind of trying to see, are there any comments on kind of thing, like every expert we are assuming that they are good, but probably experts can also do some mistakes, right? Why an expert is pulling over to the shoulder of the road, we don't know. Maybe for some other reason. So in all these works, the experts are assumed to be ideal, right?
Yeah, absolutely. That's a very good question, and that's a good segue to something called offline reinforcement learning. So what we are seeing here, as you rightly pointed out, is that expert is the best. Expert is the be-all, end-all of everything. But the question is, can you also not learn from suboptimal demonstrators? So that's where offline learning, offline RL is a very interesting recentish area, which says that I'm not going to just learn from the very best demonstrators. I'm going to learn from everybody and learn something and stitch them together to learn better behaviors. So I don't have an answer to your question about herding and other such things. I have no thoughts on that. But offline RL is something you might want to go back and take a look at, which says that we can learn not just from experts, but from anybody and everybody. Yeah.
So I think we are almost out of time. So you want to just catch up during the break? Yeah. Anyway, thank you, Ronak, for a wonderful talk.
Thank you very much.
Just a sec. A small token of appreciation. Thank you. So that's the end of this session. So we will reconvene at 4:30 after a break. Thank you. Arul Selvan Ramaswamy. Arun is an associate professor at the Department of Computer Science and Mathematics, Karlstad University, Sweden. And he decided to move back to India, and he'll be moving soon to the Department of Industrial Engineering and Operations Research, IIT Bombay. Arun is our very own. He has completed his PhD from Department of CSA under Professor Shalabh Bhatnagar. He is interested in reinforcement learning, stochastic approximation algorithms, stochastic control, and optimization. The stage is all decked up for your talk, and over to you, Arun.
ಪಿನ್ ಮಾಡಬೇಕಾ? Oh, thanks. Yeah, so thank you to Professor Bhatnagar and Professor Guhan for the kind invite. I mean, this is my alma mater and I love to be back. And any chance I get, I'll take it. Yeah, so I'm also mandated by Professor Borkar to keep it short and lively. So I'll try to sort of finish it in 45 minutes and hopefully we also have a lot of discussion. So I'm in between your nice post, scientific, dinner. So I'll try to keep it as lively as possible. Okay, so I'll start with the theme of the talk. Okay, all of this started because we had a giant research grant from the government of Sweden, and this is aimed at accelerating RL adoption for small businesses. So what that meant for us as researchers was to essentially have, have very simple RL recipes. So there are businesses and they want to use RL algorithms to solve business problems. But the thing is, when they use RL, they face a lot of technical issues. So what we wanted to do is essentially have develop a suite of RL algorithms, if you may call it that are very simple. We want it to be as close as possible to the vanilla algorithms, okay, which means implementations that are there on your Stack Exchange, implementations that are there on LLMs, right? So we want to take it and do something more to it so that we can provide guarantees, right? So that's the research part that we are truly interested in. So if you look at some of the issues that are plaguing researchers, and many of these issues have been addressed today, right? One issue is that of learning variance, spoken a lot in the morning, right? So what does this learning variance mean, right? It has many manifestations. So one manifestation is that if you train your RL agent, right, you have different seeds. A few of them give meaningful results, a few of them give junk. So what people do right now is essentially take those meaningful results, publish papers out of it, right? But when it comes to deploying it in a business, it's quite difficult, and that's a challenge for them, right? So the minute they see such high learning variance, they sort of back off. Another thing is what I call as loss peaking. This is basically what my student told, and this was spoken about by Professor Borkar in the morning, where he spoke about this grokking problem. And this is where in the later stages, you'll see your losses sort of peaking. And if you look at your rewards that are accumulated over episodes, your rewards sort of dropping and going up. And you're like, should I stop training? Or like, what is happening, right? A related issue to both learning variance and loss peaking is this thing on numerical stability. So a loss could go down, the gradients could go down to 0, but all of this doesn't mean that the neural network weights itself are bounded. So if you have attractors at infinity, if I may use that term from dynamical systems, you could have numerical instability in the sense that you'll have very large neural network weights, right? And this typically happens because there are gradient explosions, particularly in the early stages. So you'll see this problem if you use, some kind of log loss function. So if you're using things like PPO or in classical supervised learning, if you're using, for classification, if you're using log loss, right? And finally, the kind of problem that they face is that they want to use RL for decision making, but typically these decision making have constraints. So the previous talk spoke about constraints from a safety perspective, but for us there are general constraints because you can have budgetary constraints and so on. And as was pointed out before, the most popular technique is to use what are called as constrained Markov decision processes by defining cost functions. So even when you define cost function, the approaches are sort of slightly complicated. So we want to simplify that a little, right? So there are many people working on this. The first 3 are essentially students, Alexander, Anton, and Amal. Alexander and Anton and Amal's work is basically what I'll try to present today. And Anton does a lot of work on the deep learning part, not the deep RL part. So it's related, but not quite. And as you can see, some familiar names, Shala Bhatnagar and Hemachandra from IIT Bombay. We're also sort of working all of them together. Okay, so let's start with the definition that you probably saw yesterday, but without going into too many details. So you're given an experience point, right? So you have a state, an action, a reward, and the next state. A forward pass in your queue network using the current set of weights is what you're going to call as the prediction. Then you're going to use another neural network, which is a copy of your current network, but from a previous iteration, right? Previous, I don't know, 100 iterations old or something. And you're going to calculate the target, which is the right-hand side of the Bellman equation, right? And then you square it, and that becomes your squared Bellman loss. So the traditional tabular method of doing reinforcement learning relies on the contractiveness of the Bellman operator. The deep learning way of doing it is minimizing a loss function, and the loss function in this case is essentially, taking the right-hand side of the Bellman equation, plugging it to the left, and squaring it, right? Now, if we go back to the problems that I faced, right, which we'll discuss in the later half of the talk, the target network was in some sense supposed to solve at least some of these issues, in particular related to numerical stability and learning variance, right? But the problem still persists, and that's why I'm talking about it, right? So there is a lot of research which has done towards figuring out why a target network is useful. So in the initial part, I'm going to try to, in both empirical and some formal way, try to figure out when a target network is useful. Some people, for example, Kim and team, have told that a target network is completely superfluous and you should just remove it. And it hastens training, and things like the over-prediction problem of Q learning can be completely sorted out. In the mid part of the talk, I'll give a formal reason why Kim et al.'s algorithm works. And then finally, we'll talk about the this thing. Yeah. So for me, numerical instability means the supremum of the norm of the neural network weights are finite in an almost sure sense. Okay. So, I mean, gradient descent is the most popular way to train neural networks. And we are going to stick to what's popular and what's easy, right? So we start with deep Q learning, and we use gradient descent. So the derivative looks like this, right? You don't have to worry about taking derivatives with respect to this, thank God, because of the max term. Because this target network is not quite the set of neural network weights that you're taking derivatives with respect to. So what Kim et al. Says is that instead of using this max operator, why don't we use a mellow max operator, which is an approximation of the max operator, but it's differentiable. It's a C infinity function, right? So if that's the case, when they take derivatives, you'll have a derivative with respect to Q and a derivative with respect to this term as well. Okay, and then they perform regular Q learning with experience replay and all that. And they show that, at least empirically, they show that it does very well. Now, we ask this question. Sure, you can do all this, but can you just do this, right? Meaning, if we just squint our eyes and say that, yeah, since they're not lagging by much, and particularly if you choose a conservative learning rate, can I just use the original Q network instead of an old target network? So that way I can free up a lot of memory, the processing time is lower, and so on and so forth. But the question is, when can we do this? Surely not at the beginning. And why we'll sort of see in the next slide. So our conjecture is that, yeah, we cannot do it from the beginning, but maybe in the later training stages, we could maybe just use theta instead of the target network, right? That's because our conjecture is that the contribution of the target network is towards the early stages of training, particularly in stabilizing the network. Yeah. Correct. So that's why what is it a surrogate of is important. And we are claiming that this is a surrogate of the derivative, not the loss. So we'll take the derivative, and that derivative expression is where I'm going to plug in this theta. Right? And then I'm going to see, is this derivative close to this derivative? Or under what conditions are these two things close to each other? Right? So that's an important point. Okay, first let's get rid of the simple, obvious case. So can you drop the target network right at the beginning? Yeah, sorry.
So in the last slide,
yeah.
You mentioned about dropping the target network, right?
Right.
So does it then completely invalidate the need for double Q learning?
That's what we are hoping for.
Okay.
That's what we are hoping to do. We are sort of hoping to say, if you want to do reinforcement learning where there are discrete actions, there's no need to go beyond DQN. And if you want to do reinforcement learning with continuous actions, then you don't need to go beyond DDPG or SSC. So that's basically what we want to push at. Again, it's driven by the fact that we want a simple recipe for the industry. So there are people who are using these algorithms, for example, Bharat Forge, right, the municipality of Calstar. And they are engineers who are novices, who have very good deep learning knowledge, but they don't know how to deal with these phenomena. So if we can guarantee that this phenomenon will not occur and provide them with a simple recipe, then our hope is that they'll start using it. Right? And exactly that. We don't want to give them choices. If you want to do this, use this. If this is the flavor of problem, then just use DDPG. You just don't think and it should work for you. That's the kind of results that we are looking for. That's the broader goal of that project. So here is a simple problem, because I saw that there were simulations from yesterday with cart pole. So the cart pole problem, just to quickly recall, is that you have a pole. It's through a single hinge, it's on a cart, and the cart can be moved along the track to the left or to the right. And the aim is to balance the pole close to the top, right? And this is what we do. Let's say you have a vanilla reinforcement learning. We use the Gaussian error linear unit because, again, it's smooth. Later on, you'll see that this plays a role in our math. But you could use ReLU, or you'll still get the same results. The blue line is essentially when you drop the target network. So there's no target network involved. And this is the traditional reinforcement learning. It bombs big time, right? It bombs over and over and over again, right? So this has a variance component as well, over 25 times, right? It's just bombed, right? And this is, so along x-axis is the environment, the training steps, along y-axis is the discounted rewards. Undiscounted rewards every episode, right? So so red is essentially traditional RL. And as you can see, the variance is quite high. It's supposed to curb variance, supposed to make it numerically stable as a consequence, but variance is quite high. And this is not a cherry-picked example, right? This is roughly what you'll see. So what we did is we did a simple analysis, which is we decided to see the following. Let's say at some stage, not worry when, we start a parallel training thread. Right? So we've trained using a target network up to some point in time, and now we just drop it. Right? So you have two threads of training. Let's assume that you use the exact same experience replay buffer and the exact same mini batches, which means you just have experiences that you gather from, for example, the non-target network, the target network, right? Whatever you choose. And if you look at the difference between the gradients for the one-step difference, after some period of time, you'll see that the error is sort of arbitrarily small and shrinking. You can show that roughly this is in the order of the step size. And what this means is, so I have not written the forward pass Q bit because there it's easy to see. It's harder when you have this max term to guarantee that difference. But one can still show fairly easily that you have a decreasing, that it's a very good estimate. And this is what I meant when I said that I'm not going to use it as a surrogate for the loss, but just use it as a surrogate for the true gradient with a target network. This is the reason, right? Now, what happens here? Sorry. So this T minus is to indicate that this theta is the network weights that are updated using a target network. Without the T minus is to indicate that you're using the current network weight. So you're running like two parallel threads. Now, this is just the next term, right? The prediction part of the thing is still missing, but I just wrote this part because the prediction will be, in some sense, locally Lipschitz continuous.
I mean, what I'm not sure is that, have you dropped the target network or not? That
Yeah.
typically the T minus indicates the target network rate.
Sorry, yeah. So this is the training thread without the target network. This is the training thread with the target network. So if I go back, I'm going to use this, for one thread, I'm going to use this gradient, and another thread, I'm going to use this gradient. But I'm using the exact same mini batches. So that is very important. So that's why here, the reward will not come in the difference, but only the Q components. And among that, the first prediction part, which is the Q of this thing. So that I have not written it because this max is what complicates the difference. Right? Okay. So this is roughly, a very good estimate as you go later and later. And that's what we do. Is it the true gradient? No. Right? But it's a surrogate. It's a descent direction. It gives us some direction, and that direction is roughly close to the direction that you have with the target network, and you can move on. So we also checked what happens if the targets, the two threads are allowed to explore like different state action pairs, right? Then you can show a divergence, and this divergence is also slow. And this divergence depends heavily on the states and actions explored. Okay, that expression I have not written here, but it can be found in the paper. So Alex in his master's thesis did a bunch of empirical work, and this is for the cart pole problem. This plot is the following. Along x-axis is plotted the last 1,000, the first 1,000 episodes of training, okay? Along y-axis is the mean number of steps in the last 1,000 episodes. Okay, let me slow it down. So what I want to do is, I want to see after which point in time I can drop a target network, right? So here along x-axis is the point at which I drop the target network. So here I've dropped the target network at 300, 310, and so on and so forth, all the way up to 1,000. Along y-axis, this line is basically the number of steps per episode. So each episode has 500 steps. And the question is, how many steps per episode is your policy balancing? Okay, the policy that you found, how much is it keeping the cart pole straight? Is it keeping for all 500, or is it keeping for, a fraction? So it needs to keep the cart pole balanced throughout the episode for 1,000 episodes for us to say that you found a good policy. Roughly it takes around 3,000 let's say, training episodes to find the good policy with the target network. And what we find is that, roughly speaking, when you reach the 300, 400 mark, around the 10% mark of the training, you can fairly easily drop the target network, right? So here, for example, you've dropped the target network and it has found a policy which is good. So another way of looking at it is the following. Here I've plotted the cumulative rewards on the y-axis, and along the x-axis is the last 1,000 episodes, right? The red line is essentially when you have a target network for the whole process, and then the other lines are when you drop the target network, so the 500th episode and so on and so forth. So when you drop a target network, the number of episodes to find the final policy in some sense increases, right, as compared to when you have a target network throughout learning. But the actual compute time comes down. And as you can see, it finds roughly comparable policies, right? So this essentially tells us, and this is the loss version of looking at the same thing. So this essentially told us that, target networks are in some sense dispensable, and if at all they have any advantage, the advantage is only in the initial stage. So another curious thing that we observed during this experimental stage was that when we drop the target networks, almost always after we dropped it, towards the end, the sort of variance drops, right? So you don't have this kind of stuff towards the end, right? So this we are not completely able to explain. However, we have a sufficient condition to sort of enforce this, which I'll talk about later. So Alex also did some work on expert learning, which is this sort of behavioral learning which was spoken about in the last last talk. And here he essentially, pre-trained on expert behavior, and he completely, eliminated the target. He didn't even use a target network. Because all this sort of pre-training is like supervised learning, numerical stability is not too much of an issue. Again, in supervised learning, numerical stability becomes an issue only if you have like some kind of log term in your loss function. And because these are sort of mean squared errors, you don't really need a target network. So if you do expert training or offline learning and then move on to online learning, you can just ditch target networks altogether. So, sure, that was some empirical work that we did, and it sort of gave us the confidence that, yeah, we can now go along the lines of what Kim et al. Are doing, and we can try to get rid of a target network. But what we did earlier was to get rid of a target network after some point in time. What that point is, we have no idea, so it's not really a recipe, right? So it's a good path forward, but it's not really a solution that we were looking for. So we wanted to come up with an algorithm that got rid of the target network while using our surrogate gradient. And we wanted to do it from the beginning, without really sort of this pre-training and so on and so forth. So the first important component in this recipe was this activation function that we built. And this was done, to collaborators from IISc. So we took the GALU, the Gaussian error linear unit, which is given by blue. And what we realized is that the learning variance, there is a component in the learning variance that comes from the forward pass. And this is a consequence of using activation functions that have unbounded support. So what we did is just truncated this GALU, and we called it the truncated GALU activation. So the advantage of truncated GALU is that it's got compact support. It can be asymmetric, meaning it saturates at different points. So here it looks like it's saturating at 2, but you can like specify different points of saturations on the negative and the positive side. And it's C infinity. So it's like infinitely many times differentiable. We looked at this surrogate loss, and right from the beginning, we didn't want to use a target network. So what we did is we clipped the gradient. So there are two components to where a variance arises. The variance arises through the use of unbounded support activations, and because the neural network weights themselves are quite large, right? Which indirectly impacts this particular thing and this. But what we found is essentially that if you stabilize the output layer, then that in some sense bootstraps into stability for the previous layer. So that's what this clipping does. So this is the traditional clipping, but only done for the output layer. Okay. So let's do a sort of quick variance analysis. And here, for the sake of simplicity of presenting, I'm going to assume that I'm just going to clip for all the layers, right? So again, to repeat, we're just clipping for the output layer. But for the analysis, I'm just going to say I'm going to clip for all the layers, right? So I'm going to first define what is called as my update martingale. So my update martingale is essentially the clipping minus its expected value. Again, of the clip term itself. There could be some kind of noise. You know, we sort of don't bother with that. This noise, again, this has a story behind why this noise appears. For now, you could sort of discard it. You define a filtration in sort of the natural way. All the information that you have at time n in order to make your update, right? And what you can show is that this update martingale is indeed a martingale, right? In that if you condition on the past, you get the best you can do is look at the past information. The expected mean is in some sense 0. The more important bit is that the martingale differences are bounded, right? Here I've used absolute terms and not norms because I want to do a component-wise analysis, but it should also work with norms. So the minute you see this component-wise bound, you should just use Hofding, and that's basically what we did. So when we used Hofding, what we were able to see is that the tail is bounded by this exponential term. And this looks like a Gaussian term, right? And this means that the variance in some sense is also bounded. You'll see that you have this summation of the learning rate terms squared here. And just as it was done in the talk in the morning, we use the Robbins-Monroe scheme, which means that the summation square is finite, right? And this is the clipping constant, and it appears sort of neatly like this. This is a noise term that we add if we want to escape saddle point policies, right? But it doesn't affect the variance. So the good thing is that typically the variance grows with time, which means that there should be an end term here somewhere. So as you keep training, your variance should sort of keep growing, right? And because you sort of clip, the variance is arrested, right? And it's independent of time, so you can train it for a very long time. So, like I said, we only clip for the output layer, which means that this analysis is technically only valid for the output layer. Or if you want to do the same analysis for the previous layers, you need to condition on the stability of the output layer and keep going back layer by layer. What you'll see is that the variance, although independent of n, will be dependent on the neural network weights of the forward layers. Right? So as you go back, in some sense, the learning variance is. So this is something that we're doing both with Professor Bhatnagar and Professor Hemachandra from IIT-B, is we're trying to use simultaneous perturbations in Q-learning to train neural networks. So there was this paper by Sanjeev Arora and his team, which essentially said that such kind of zeroth optimization methods are very fast for training, for fine-tuning large language models. They're indeed fast, and they're also fast for Q-learning, right? On top of that, we've analyzed, it's a different paper and a different talk, that SPSA, with some extra bit can get you out of saddle points, right? Not degenerate saddle points, but strict saddle points, which is a problem in reinforcement learning as opposed to deep learning. So even in this case, such an analysis goes through, provided we clip the gradients. Okay, so that was with regards to variance. Now let's look at loss peaking. So loss peaking is this phenomenon where your loss function keeps decaying, and then it sort of, there's a peak, and there's another peak, there's another peak, and it keeps going down, right? So here, I'm going to pivot into the Kim et al. Paper, which uses the Mellomax operator, right? Why do I need it? Because I want my Bellman loss to be L-smooth. What is L-smooth? The gradient, the loss gradient is essentially Lipschitz continuous. Not Lipschitz continuous in the global sense, but Lipschitz continuous in the local sense. So if you have L-smoothness of the Bellman loss, as long as the sample gradients, right, you choose your clipping constant such that the sample gradients are in some sense a good indicator of descent, right? So you have an expectation hidden in your true gradient, and that is your true descent, right? As long as your sample gradient has some impact on the true gradient, you can use the super-martingale convergence theorem because the loss function is a positive function, it is bounded below, and you can show essentially that if you take your loss, the loss is decreasing, right? The loss in the next step is less than the loss in the previous step, minus some very small quantity, which decays as the square of the step size, right? So you can take step sizes of like 1 by n or something. And again, we don't want the step sizes to decay every learning step. As long as it decays, I don't know, every few episodes, that's sort of good enough, basically what deep learning people do, right? As a consequence of this, we essentially have that the loss converges. So you have stability in this sense, meaning that your loss doesn't blow up. All this has an underlying sort of implication on how we initialize the neural network weights. But again, if you have L-smooth loss functions, again, locally Lipschitz continuous, you'll be able to show these things, right? Then someone spoke about the Robbins-Siegmund theorem. So there's a lot that I'm skipping here, and we could sort of take it offline or later. So the Robbins-Siegmund theorem essentially yields this thing, which is that the square of the norm of the gradients are summable. Summable in what sense? Summable in the sense that, when it's multiplied by an, it's summable, not in the sense where it's summable by itself. And this is important because we can show that the gradients are vanishing. So the loss is vanishing, sure, but why should the gradients vanish? Right, so that's also equally important. And if you're asking, what are you taking what is this eta? So it's essentially the ergodic occupation measure. So it depends on what data you use for training. So the loss gradient, there should be a gradient here. So the loss gradient is, so the loss is vanishing, the loss gradient is also vanishing, right? And all of this stops short of what Gohan was asking, what is numerical stability, which is that the neural network weight should be bounded, right? So both these things don't imply that the neural network's weight should be bounded. Your weights could still be drifting off to infinity, right? Now, if you want to stop that, then you need to use some kind of regularization. So you make the loss coercive. So you know your loss is decreasing, right? So if you make your loss coercive, then it means that if your neural network weights are increasing, then by definition your loss needs to go up. So your loss is sort of going down, it means that your neural network weights are not increasing to infinity. So that essentially gives us numerical stability. At a cost, at this cost. Right? You're not going to find, in some sense, a true, for the lack of better word, degenerate saddle point or minima. Right? You find something lagging, but in like practical settings, this is what we like. So this is coming back to the cart pole problem. This is the training. This is the same plot, right? Essentially, the blue plot is the new algorithm, and the red plot is traditional neural network training. As you can see, the rewards are also slightly better, and the variance is lower, right? So we've applied it to other use cases. So here is a use case from Lunar Lander. So this is our algorithm. This is sort of traditional reinforcement learning. These are cherry-picked examples in the sense that we didn't really try hard to get either of those results. So we did some training, whatever result we got is what you're seeing, right? So it's not cherry-picked in that sense, but it's probably not fair for the traditional training, because maybe if you had trained it longer, it would have performed better. We don't know, right? But we just trained it quickly and stopped at it. So I want to shift gears, and I want to talk about constraints in reinforcement learning. And for that, I want to quickly introduce the problem, run to the algorithm, and show you a couple of results, and I want to wind it in like 5 to 10 minutes. So Amal has a project that's undergoing on from an energy company, where they want to build an AI to manage a single building. They are control theoretic people. So you want to do things like you want to charge batteries, you want to charge your cars, like your Teslas or whatever. You also want to control the HVAC system to optimize power consumptions. And you have several constraints. So you have constraints like battery constraints. Like I said, they're also interested in secondary control, right? So there are constraints from power systems. There are comfort constraints, like you can turn off and on the heating, but are the people getting cold or not, right? That kind of stuff. So the RL environment for this kind of work is this thing called as CityLearn. But the problem with CityLearn is that it doesn't focus a lot on constraints. So what Amal did is essentially build a new framework, if I may call it that, we call as Safe CityLearn, so that you can incorporate. So there's a lot more focus on the constraints. This is the rough architecture of CityLearn. And the thing is, you can do research on energy systems, and you can compare your algorithm to sort of known baselines. You can get a KPI comparing your algorithm to other algorithms and so on. So that was the algorithm. We saw that there were no benchmarks. So we benchmarking framework. So we built a benchmarking framework. So that is one thing. And if you want to use it, it's sort of freely available online, and it's integrated into OpenAI Gym. And so it's easy. If you've been using those things, then basically it should be easy to use this. So like it was said in the previous talk, what constrained RL does is that you want to maximize the policy, right? You want to find a policy which maximizes the value function such that a cost value function is below a certain budget. So I use this term on purpose, right? So V is in some sense the reward value function, VC is in some sense the cost value function. Pi is used to indicate that the policy pi is used to calculate these values, and this cost is associated with pi. Both are discounted. Okay. Now, if you're given a policy pi, you want to evaluate its performance, meaning how well it's doing in terms of reward. You can do a simple forward pass, let's say on your DQN, right? But if you want to evaluate constraint satisfactions, then what do? You can't really do a forward pass on this. So it doesn't exactly make sense. Because what would this look like, right? What you can do is, which is popularly done, is to perform a few rollouts, which means you play your algorithm out in your, you play the policy out in your environment and see what's the cost, right? Or you could say that I'm going to take the reward, I have a single stage cost, and I'm going to calculate this effective reward, and I'm going to just do Q learning on that. So this is penalty-based Q learning. It works sometimes, it doesn't work all the time. Certainly not in safety critical applications. So what Amal did is essentially, because we are in the setting of, constraints are very important to us, right? So what Amal did is essentially do the following. You want to pick the best action, but you want to in some sense be prepared for the worst. So she trained two networks, a reward network and a cost network. The reward network tries to find the policy which maximizes the reward, and the cost network tries to find the costs associated with the policy which maximizes the cost. It does very badly, right? And then you have a policy network. And the policy network essentially tries to balance it out, right? So it tries to maximize the reward while trying to make sure that the cost constraints are satisfied. But the cost is not associated with the policy, but the cost is associated with the action that you take with the policy in the current step, followed by which you assume that very bad actions are being taken, right? And then you have a traditional Lagrangian update. So this is the half cheetah algorithm. As was explained earlier, there's a velocity constraints. And this is being in the gray region essentially means that you're just on the border of the constraint, just below it, right? If it's green means you're sort of well below the velocity constraints. This is, I think, the algorithm. So this was our algorithm which is running, and which is now running to the right was an algorithm called RCPO, which came from, I think, one from Technion, right? So it's a lot faster, but it just goes a little above the constraints. So it's in red because it's a little above the constraints, right? So this is again sort of quick comparison. The last two are essentially our algorithms. This is using traditional ReLU. This is using this bit that I explained earlier, where we have this activation function, we clip, we add noise, all that bit, right? You see that the variance is not increasing, but there's a slight improvement in the reward. So this is the reward, this is the cost, this lower is better, this is the constraint satisfaction rate, and this is in some sense the variance. This is the training process, right? On the left-hand side, what you see is essentially the rewards over the training. You train it for 1 million steps because that's, in some sense, standard when it comes to dealing with OmniSafe. So this is the rewards, and this is the constraint satisfaction. So so that velocity constraint must be below for some 25% or something like that. So this is the constraint line, right? So you see this green curve, which has the highest reward, right? So this is pretending that the constraint doesn't exist. You just maximize rewards, right? And this is, as you may know, the SAC algorithm, right? The blue curve, on the other hand, is our algorithm. Comparable, you have the SAC lag. So it's the SAC algorithm with the Lagrangian update. That update relies on rollouts in order to calculate its cost. Because we, in some sense, prepare for the worst, you can see that the constraint satisfaction is also is pretty good. So the blue curve is our constraint satisfaction. And you see that it's well below the line as opposed to, for example, SAC lag, which was in some sense the benchmark that we were trying to beat, which initially was above, and towards the later stages of training, it comes below. So here you see that the variance is quite high. This is because these results are from when we use ReLU. So we used our algorithm, but ReLU, right? But if we do all this trickery that we did for the DQN to this scenario, then essentially what I would like you to sort of point out, notice is the constraint satisfaction. The constraint satisfaction is practically, I mean, it's satisfied all the time. It's unfortunate that Amal went on a holiday right after she got these plots, because a video for this, in my estimate, I think with the half cheetah, we would have got sort of a green dot all the time, right? So here the variance is not plotted. Apologies for that. But we just use 5 seeds, right? And we use 5 seeds because that's what the OmniSafe benchmark also does, right? However, we calculated also with like 25 seeds, and the variance is not any different. Right. So to sort of quickly conclude, and to keep my promise of keeping the talk short, what did we see? So we saw a modification of deep Q learning, right? It was just deep Q learning. We clipped it. We added a new activation function. Everything goes according to what you get in Python libraries, right? And we were able to prove some properties for it, right? What was clear from the video was that its performance is better, but what I can't illustrate is that it was a lot easier to train as compared to traditional DQN. Anton, like I said, has applied the same technique, but transcribed it to deep learning problems, and we have a paper that's currently under review for that. Finally, we have like a very simple way of dealing with constraints. At least we think it's simple, because again, it's easy to train, particularly with this bit of using, the truncated GALU and clipping the gradients. And so it's sort of, if you do these things, it's not hard to, find learning rate. You don't have to like fuss over it over days, right? It's like a couple of hours and you have your results. Initially we thought that this sort of constraint, our algorithm would be too conservative, as it is sort of seen over here. But it also somehow learns the rewards well, right? The math for this part is not yet ready, is sort of ongoing research, and we were sort of looking into explaining this phenomena, right? So with that, I'll stop, and I'm happy to take any questions if there are any. Thanks.
Sorry, I'm not familiar with GALU.
Yeah.
Did you at any point show the formula for it? And can you explain what is the advantage of GALU in the results that you have shown?
Right. So I've now, as I'm speaking, I realize that I've suppressed a bit too much. Probably I should have maybe focused on just this one bit. So GALU is like a smoothened version of ReLU, right? What we are calling as truncated GALU is that we take this bit and we also flip it at 0. So this bit is also what is going down, right? And we take this and sort of attach it here and here. So we sort of shift it, and then, so it's a sort of essentially a smoothened version. And why is this important? this is important, not here, not for variance, but here. So if you take the Bellman laws, there are two issues. One is the max operator. The max we can get rid of, approximate it with mellow max. And the approximation is pretty good, so I'm not going to discuss it. The other sort of bottleneck is the forward pass. And if this forward pass has things like ReLU, then it's not smooth. And we wanted the gradient to be Lipschitz continuous, not in the global sense, but in the local sense, which it is if it is GALU. So you could use sigmoid in theory, and it would still work. Empirically, however, we saw that it doesn't work. So that we don't know why. Maybe because of the same reason why larger truncations provide better descent, estimates as opposed to smaller truncations. The same with the activation functions, because we use sort of larger compact supports. So it did not suffer probably from the vanishing gradients issues. So the performance was better, but the theory is applicable even if we use sigmoid, tan H, and so on.
Thank you.
Still have.
Thanks for hi Professor. Thanks for the the good talk. So I'm a bit unclear on how this DQN was applied to half cheetah. So this has like continuous actions, right? So
right. So this is not DQN. So we modified DDPG.
DDPG, okay.
So I'm sorry about the notation. I'll blame Amal for it. So this is essentially what the policy network tries to maximize. And if you ditch this term, then you see that it maximizes the Q function. This is your traditional DQN, right, which is your critic. This is like your actor update, right? Now on top of that, you need to take care of constraints. So you apply the Lagrange multiplier method. So that gives you this as your, objective to update. You also need to update the Lagrangian, which is done this. So this is, in some sense, not something that was, is that new? What people do, for example, I think even you have a paper, right? So even Bhatnagar has a paper where he updates the Lagrangian like this. And if I'm not mistaken, Amal took the inspiration from his paper. But what they do is they perform a rollout in order to estimate the cost, because they want to estimate the cost associated with the current policy. We were like, let's be conservative. Let's associate the cost not associated with the current policy, but with the worst case policy. So you have like a friend who is a total wrecker, right? You do your best in the current step, and then you let him go loose. Now you want to take an action which maximizes the Q function, but you also are going to have your friends back. You will let him loose, but you are going to make sure that he still remains within the budget, right? So that is, in some sense, the inspiration to do this. And the fact that it is simple. Now it's just 3 neural networks. Before you had 2 neural networks, now you have 3 neural networks. I don't have a picture for the architecture, but the gradients and the way they back propagate is also sort of interesting to see. And we do some skipping. If you've attended the morning talk by Professor Borkar, he spoke about residual. So we do that. And as a consequence, I believe that as a consequence of all that, we get results that are slightly, in some sense, better in terms of reward as well. Because, like I said, we just expected good constraint satisfaction, and we were hoping for the rewards to be comparable to, the benchmark, which was SAC with Lagrangian. But yeah, we got sort of slightly better results, so we are happy on that. We don't know why yet. So here we don't know the math, right? But I believe that it's somewhere in between the 3 Bs, Borkar, B-name, and Bird-Checkers. So I think the answer sort of lies somewhere there, and we're sort of going to look into it. Thanks.
I think we've reached the end of the day.
Thank you.
Thank you, Arun, for the great talk.
Thank you. Thank you so much. Oh, thank you so much. Yeah. Thank you.
And thank you all for your attention. Just a reminder that there's a cultural event scheduled at 6:30